Okay, so in this introduction, I will explain briefly the motivations and rationale behind our work to develop COMPS. So the idea of our work of the developing COMPS and PyCOMPs comes from the need of dealing constantly with new with developing and executing application on new architecture that are becoming, as you know, more and more complex from the point of view of the how to access the resource itself, okay, and also due to the heterogeneity of the architecture. You know that now also the supercomputers, for example, my notion that we have here is not an homogeneous architecture. We have GPUs, we have CPUs, we have FPGA, etc. So we have to deal with applications that are usually deployed on quite heterogeneous architectures. So we need to have a programming model that could let us develop application transparently to all these heterogeneous architectures, because of course the developer cannot stay always behind the new release of new hardware. And also, as I said, we have to deal also on, for example, with when we talk about cloud, with the new APIs to access those resources. So we have providers with Amazon, Google, etc. They have their own API. So again, we have to face those challenges on behalf of the developer. Many of you are scientists, of course, so you have to deal with your science problem and not with the intricacies of the infrastructures. So a part of this, we take care also on how, not just on how to program and execute the applications, but how good is the development of that application. So we talk about efficiency. Is the application that I program efficiently executed on a given infrastructure? Just running doesn't mean that the application is okay. So above all, when we talk of HPC, we want that the application efficiently uses all the cores, all the CPUs that we have available. Okay, so efficiency is an important constraint that we have. That's why a big part of our work, when also talking with you users, is to tune the application for the architectures in a way, and we will explain also during this training how you can, using other tools that we have, how you can control the behavior of your application when executing on a given infrastructure. So in this way, you can see that the application is not just running and maybe also running in parallel, but how efficiently is using the nodes of a cluster, for example. So now, as I said, the challenges are growing every day, because it's not only the architecture part of the problem. So it's not the pure hardware, but also the fact that, for example, we are now dealing with resources that are dynamically available. This is the case, for example, when we deal with application that runs on the so-called computing continuum. Computing continuum is an infrastructure, it's the deployment infrastructure that considers not just cloud or clusters, but also IoT devices, is called edge, often it's called edge devices. So edge devices are mobile phones, or sensors, for example, that are available in a car that is connected. So those devices now are more and more capable in terms of computational power. So we have, nowadays, we have computers. The mobile phones are computers itself. The cars have a lot of GPUs now installed. So they are mobile computers, and we have many applications now. We are dealing with projects where the applications are spawned across this computing continuum. So the application, for example, is started where the data is generated, close to the sensors, okay? And then parts of this computation is offloaded to a cloud, because, of course, those devices are enough powerful, but not for all the kind of applications. So now we have to deal also with the dynamicity of the availability of resources. Of course, in this case, heterogeneity is another factor that we have to deal with. And we have, in this computing continuum, of course, we have a network, different type of networks. These include not just the network itself, but latency, instability, etc. So that's why it's important to have a programming framework that could give us fault tolerance in case part of the application is failing because of unavailability, sudden unavailability of resources, etc. We have to take into account power constraints. Again, these devices have power constraints, so we have to take care again that first of all we need to compute in a power efficient way, and also again we have to consider that the battery will be drained, okay, and we have no availability of the resources. So in this picture you see that now we are dealing with this kind of projects also. So applications that are executed across the computing continuum. Since the beginning, our idea, as you understand, is to act on behalf of the user to make his her life easier. So let the user be far from the intricacy of the architectures of the computing infrastructures, and let them focus just on their problem, on their scientific problem. So we what we do is to develop tools that are middlewares, so intermediate layers, that take the difficult part of the accessing the infrastructures and distribute the work across all those resources, dealing with the intricacy of moving data where the nodes are available, scheduling the parts of the application on the proper node, and automatically also improve the performance that we will see, because with COMPSs we don't just distribute, as you may know, the applications, but we automatically parallelize the sequential applications. This is the core of COMPSs actually. And on top of this, as I said, we provide also tools for visualizing the performance of the application through real-time monitoring of the execution. We have a monitoring dashboard, and also we have performance analysis that we call the post-mortem analysis. So once the application is executed, we can have a look at what happened in the very detail of the threads of the data, how data is moved, how the task, the part of the application are balanced across the nodes, etc., to improve efficiency, as I said before. And also now we, of course, we are working a lot with the integration on workflows with the machine learning and data analytics code. That's why also we developed a parallel machine learning application, dislib. That is also part of the afternoon training today. Dislib is a parallel machine learning application which is built on top of PyCOMPSs and gives you already developed algorithms. So in this picture, again, it's a summary of what I said. We have the application that have the program logic, so your workflows, independent of the underlying platform. So you just focus on your workflows, on your science, and with the programming model layer, which is a high-level, clean, abstract interface that, in the case of COMPSs, is task-based, as we will see. And then we have the runtime, which is the smart part of the COMPSs programming framework, which is the part that deals with the access to the infrastructures, with the data movement, with the scheduling, with the power efficiency, load balancing, etc. And then this runtime has different interfaces to talk with the Mare Nostrum, with a grid, with the cloud, or with containers, etc. Okay, so that's why this box is bigger, because it's the smart part that contains the big part of the power of COMPSs. And this is just a bit of history. The COMPS comes from a long time scientific research on programming models. The COMPS belongs to the star superscalar family, which includes also the OMPS programming model. The difference is the target. So with COMPS, we are dealing with the distributed infrastructures as cluster grids or clouds, where the tasks are, the granularity of the task is from seconds to minutes, etc. So we have a longer, higher granularity task that shares, this task shares data in forms of files of serialized objects. While OMPs, we are talking about node parallelization, where we have a smaller tasks that run on GPUs, on shared memory nodes, okay? And we have a very small task in the order of a duration of 100 milliseconds or microseconds. And the dependencies are not files or objects, but are in-memory data. And with the COMPS, we deal with the Java, C++, and now the days more and more Python, while OMPS is generally for C, C++ and Fortran application. So this is the motivation. So COMPS. The idea of COMPS is to have a sequential programming model. So COMPS is not a programming language, of course. Is a programming model where the code of the user doesn't have to change mostly. Okay. The idea is that the user still keeps the consequential, but the user, the developer, has to think a bit in parallel, in the sense that through the some annotation that we will put in the code, the developer is helping, let's say, the COMPS runtime to identify the parts of the code that can be executed in a node. Is what we call the task. So task is for us the unit of the work, and that's why we call the task-based programming model. So it's a simple linear address space, so you don't have to change how you access the data. Your application, as I said, is the same. And based on the information that we give in the code, okay, the runtime builds a task graph, which is something like that visually, okay, that contains the type of nodes, the type of of tasks that are to be executed, and the data dependencies between those tasks. So implicitly, we are building a workflow. So COMPS is not a workflow language. There are several in research. There are several competitors, let's say, where you explicitly define express the workflows. In our case, is the dependencies are automatically detected at runtime by COMPS through the annotations. So in those annotations, we will see you specify if a task has 3 parameters, 1 integer, 1 string, returns an integer, a string, etc. So through those dependencies and through the calls to those tasks, the runtime builds the dependencies, they resolve the dependency of behalf. And when there are tasks that are free of dependencies, those are executed in parallel. So the execution is in parallel because there are no dependencies and there are enough nodes where to execute those tasks. And the important part is that the code that you annotate is agnostic of the computing platform. Said for us, it's important to give you a flexible tool that is independent of the architecture. So your code runs everywhere. Again, of course, you have to. It's not the same running an application Mare Nostrum than in a cloud, for example. In that case, we are talking about improving performance, balancing the load, etc. But in principle, the execution of the code is always the same. So we, as I said, we will see tomorrow, a part of basic type of tasks, so your sequential code, which is executed in parallel. Task can be also other parallel applications. For example, you can introduce as task an MPI application. So These tasks that internally have another level of parallelism through MPI or OpenMP. Okay, so this is automatically scheduled by COMPS. We have, of course, integration with our brother OMPs, so you can mix COMPS and OMPs code, and you can also have a streaming task. So not just simple tasks, but you can have tasks that are living as long as there are streams coming in and out. We support failure management, as I said. We have parallel machine learning, and etc. COMPS is available in production in Mare Nostrum. This means that everyone who has access to the supercomputer can use COMPS without the need of installing. But also COMPS is available in other supercomputers in Europe belonging to the PRACE supercomputing network. And also it is available in PGI, Federated Cloud, and in the United States in the Chameleon Cloud. So this another picture that a bit summarizes the idea. So the applications are annotated by the developer. These with Java or Python annotations. Once the application is executed, so you write your code, you annotate your code. At execution time, there is the runtime. Let's say there's a big box because there's several components inside. First thing that the COMPS runtime does is analysis of the task dependencies. So this happens because unless there is a sort of barrier, your code is executed like immediately, in the sense that all the calls to the tasks are intercepted by the runtimes that analyzes the type of task, the data, the dependencies, and build that dependency graph, okay, which is a representation of the execution of your code. And based on this task graph, COMPS schedules then those ready to run tasks on the available nodes, monitoring the execution, retrieving the data, okay, and also managing the resources. Managing the resources means that, for example, in cloud, simple example, you can add or remove elastically nodes. This is a typical feature of the clouds. You can ask for more resources depending on the load of the application. And it's important because above all in cloud, you pay for the resources that you use. So it's important to have this elasticity capability to shrink or enlarge your pool of resources depending on the actual load of the application. In this case, as you can see again, this picture, I want to highlight the fact that the parallelism comes from the runtime execution of the application. You can think, or you will see a lot of code today, those green task is the same task in your code, which is executed, for example, in a for loop. But because of the dependencies, when you call each iteration of the loop, the tasks are independent between them, okay? So, for example, you have a for from 1 to 100, okay? Those 100 tasks are independent because they receive different parts of a data set, for example, so they can work independently. And because we have a lot of nodes, for example, in a cluster, a lot of CPUs, you can execute them in parallel. So this is what we call inherent parallelism or implicit parallelism in COMPS applications. So this is what I said before. On top of the execution management, then you can have a look at the traces, we call traces, which is the post-mortem analysis of COMPS applications. So these tools, which is called the Paraver, analyzes what happened at execution times, what happened in terms of data transfers, task executions, threads, etc., etc. So you can see if the application is well balanced or not in the end. Okay, so how long a task lasts, etc. We have a monitoring dashboard where you can see on real time what is happening. So, for example, this graph is built dynamically. As long as the execution advances, you will see those bullets, okay, scheduled and executed. And also you can see at the end all the logs eventually. You can see for each of those tasks, you can see, for example, if there was an error or etc. We support Jupyter notebooks, so you can execute interactively, as you will see after. You can execute PyCOMPSs application using Jupyter notebooks. So this is a general introduction. Don't be worried because we will go in every details during these 2 days. So in general, our aim is to provide a workflow environment that enables the integration of different kinds of computing paradigms, and from HPC to machine learning, data analytics, etc. And then we have the programming model, which is the glue, provides the glue to integrate all those kind of computations. And we spawn dynamically those workflows on different kind of resources, dealing with different technologies, for example, with Queue Manager as LARM in Mare Nostrum, with the Unicore for the execution on grids or other kind of clusters. We support different kind of containerization technologies as Docker, Singularity, which is the container technology for HPC usually. And those applications, those high-level applications, then can be executed transparently on different kind of infrastructures without touching the scientific part of the problem. Of course, you have to configure an application, a COMPSs application, to know that there is an edge node, a cloud, or a supercomputer. Of course, but it's separated, the configuration of the execution with the programming of the workflow. So we develop and improve COMPSs above all in different European projects. So many of you here are from DTGO. Now we are in the final year of a sprint project. We are with Rosa coordinate the flows for HPC project, and you know that in DTGO we will inherit a lot of the work from flows in terms of workflow development. And so we like to depict our group as a task graph. So you will meet a lot of people during these days. Yeah.
Okay. Hello and welcome to the second session of the PATC COMPSs tutorial. I guess that you see already my screen. It is being shared. My name is Javier Conejero, and I'm going to show you in this first session how to develop or how to parallelize your Python application with PyCOMPSs. In this first session, I'm going to dive into the PyCOMPSs programming model using Jupyter notebooks in order to show you with very, very simple examples how to define your tasks, how to run, and how to parallelize your code. In the next session, which will be after the break, then we will have a hands-on where we will play with the lessons that we have learned during this session, and you will be able to play directly with your laptops, directly with the code and play a little bit with PyCOMPSs. Okay, so first, let's start. There are a few things that are important to take into account with the PyCOMPSs, which is it is based in Python. Well, it supports multiple languages, but for the sake of this session, we are going to focus in Python. And it is based in Python sequential code, okay? And we have a mechanism to define what are going to be tasks, which are going to be considered the units of work. And these units of work will be offloaded to the runtime, which will execute them in distributed resources. We don't care where they are or how to define them at this point, because we are going to focus on how to develop the application and how to define those tasks. Okay, so these notebooks are available in the repository, so you will have all of them available afterwards, and you will be able also to play with all of them if you want to recap or to have any question. Okay. The very first thing is, I guess that you already know Python, or you have some knowledge of Python. The first thing that we provide in order to parallelize your application with Python, with PyCOMPs, is a library which is called PyCOMPS Interactive, that you can import from a Jupyter notebook and will give you the ability to start the runtime and to stop the runtime while the Jupyter notebook is running. I want to point out here that this is not necessary when you are parallelizing a Python script. This is only for Jupyter notebooks, okay? So you will see that in all Jupyter notebooks, we import this PyCOMPS Interactive as PyCOMPs, and then we call to the runtime start, okay? And at the end, we will see how to stop. Just to remark, this will not appear into the plain Python scripts. We will see it then later. Okay, so the first thing, we can import this library and we call the start. Here, maybe you see that this is a little bit too much for starting, but the only important line is this one, which is going to be executed, which is ipycomps start. And then it is followed up by a set of arguments that can be defined in order to tune the runtime parameters. For example, in this at this moment that I am going to start the runtime saying, I want you to generate the task dependency graph because I want to see it afterwards. And I want you to monitor or to put the information in the monitor every second. Of course, there's a ton of parameters, like for choosing scheduler, where to write temporary files, and a lot of parameters that can enable you to deal with complex infrastructures. But at this point, we want to keep it simple. There are two more that are interesting and are important to know, which is the debugging. If you enable debug true, it will create log files that enable to find issues, errors, and what happens if something fails. And tracing, which trace equals true, which enables to generate the postmortem tracing analysis. Okay, we will see more details on these two in next sessions. But okay, let's focus on how to define a task. When we start the runtime, we will see our Flower latest version released in November 3.1, and it says that the login path it's in where it is. Okay, I am running in a container that you will use in the next session. So this is where all the logs will be. Okay, here it is where the things start to getting interesting. We have the mechanism to define what is going to be a task. We make use of Python decorators. Okay, so you can guess that every function that you define in your code can be decorated with our task decorator in order to define that piece of code, what is going to be a task and consequently a unit of work. Okay, so you can see that by importing the task decorator and placing it on top of any function that you want, that we are going to define, for example, this function square, that it is going to be a task. It's going to become one of the circles within the task dependency graph. And it will have some inputs and outputs, which are the arrows that we have seen in the task dependency graph. The important thing here is that whenever you define a task, the runtime will inspect into the task definition and the task returns in order to build that task dependency graph, so that you don't have to deal explicitly defining what the parameters are. So the task decorator placed on top of any kind of function will declare it as a task, okay? And this task decorator accepts a set of parameters that can be also important in some cases in order to define the behavior of the task itself. For example, one of the most important or more interesting ones is the returns, which is going to say, hey, this task, which is called square, is going to return one element. This is necessary because Python doesn't have type hinting, well, doesn't have types like C or C++. However, if you use type hinting, it will also work in this way. Int. This also will be accepted, but this was introduced in the latest versions. To keep it simple, we just keep the parameter here in the task decorator. Okay, so once we run these cells, we just declare them, but we are not running them. So I just want to be clear with this. We have declared 3 tasks that will be taken by the runtime in order to execute the application. So whenever we invoke those functions, instead of being executed like sequential Python code in this notebook, they will be sent to the runtime, and the runtime will decide whether to submit it to a worker or to another place. Okay, so if I run this, he says, I have found a task, square. It has directly offloaded to the runtime, and it is being executed into one of the worker processes. If I run the second one, yeah. It is launched to the runtime, and it is going to be executed with one of the workers, and with the and the task is free of dependencies. I'm going to show that in a bit. Okay. These 3 tasks, if I submit them, they seem that they are going to be executed at any time in one of the workers. But please note that this first task is invoked with one input, which is number 2, and it produces A, which is the result of that task. The next task is add, consumes A. So there's a data dependency. So in order to have a result that is valid, task add has to wait for task square to be executed. So this is the way that the runtime is building the task dependency. And even though it seems that all of them are launched at the same time, not all of them are executed at the same time. We have to respect those data dependencies in order to ensure that the result is valid. Okay? And the last one, which is multiply, has an input B, which is the result of add. Okay, so we see that there's a linear dependency, and square will be executed first, then add, and then multiply. I'm going to show that later on. So with this, the execution will be the execution of the task are offloaded, and I want to point out in this notebook how to declare them. In the next notebook, I'm going to show you exactly what happens with that data dependency. Once we have finished all our algorithm, which is invoking those tasks, in a Jupyter notebook, we have to stop the runtime because we are going to jump to the next one. And there's a parameter here, which is called synchronize, which grabs all the data that has been produced remotely in one of the workers. This is important to consider. And I'm going to show you in the next notebook. So the results are here. Okay?
Sorry, synchronization.
Synchronization thing is something that I'm going to explain in the next notebook. But briefly, synchronization is bringing the data that has been produced in one of the workers to the master. Okay, so
When someone asks a question, if you can repeat, if not the people who's in the chat.
okay, sorry, I will repeat that. Okay. Okay, thank you. Okay, let's move to the second notebook. This second notebook is exactly the same as previous one, but introduces the concept of synchronization. Okay, so I'm going to skip, I'm going to run the initialization. It is exactly the same as in the previous notebook. And here in the imports, we see that a new one has appeared, which is COMPSs. Okay, since the tasks are submitted to one of the worker nodes that may be here in my laptop or maybe in some other machine, whenever a task is executed, the data is computed in that remote node, and the data is kept there so that we can exploit all the main memory from all the nodes at the same time. Okay, imagine a task that produces a very big object. Okay, if we run all those tasks in my machine, I won't have enough memory. But if we launch that function as a task into several nodes, it can be using the memory of multiple nodes. And then once I have the final result, I can get the final result, which may be like a small piece of all of them. Okay, and this is why COMPSs comes useful. If I declare the same 3 tasks that in the previous notebook and I run them, here we will see what happens. A, B, and C with the same dependencies, and I want to retrieve the value of C. This will go to the node where it has been produced that data, bring it to the Jupyter notebook, and then we are able to play with it and check. And I want to remark this. We have been playing with A, B, and C, and we have just synchronized C. So if we print the results of all these 3 variables, we see that A and B are still future objects. They are in a remote place. However, C has been brought to the master and we have added 1. So the value is here. If we want to check the value of A, we can wait for A, bring it to the main process, and then we have its value. If I run again this cell, then 4 is here. Okay, so, and if I stop the runtime and I want to synchronize everything, it will detect that B is still a future object, which is the way that we call the objects that have not been brought to the master. And then we have all of them here. This moment, I want to make a stop and focus in 2 things. In the PyCOMPSs programming model, we have 2 main concepts, which is the task declaration and the synchronization. And these are the main key features to parallelize almost any application. Okay. With regard to the data dependencies, we can see what happened in the runtime. I am advancing a little bit to show you what happened. This is the monitor where we can see the information of what happened under the hood of COMPSs. Okay, we see that we have run in my machine with 4 computing units, and we can check the complete task graph once the application has finished. Okay, so here we see the task dependency graph that COMPSs has extracted from the application. If we go back to the application, we see that well, this hasn't been very well drawn, but we see that the parallelism. And the monitor also enables us to give us a little bit more information about the execution itself. Okay. One cool feature of the monitor is that you can see during the execution, as Daniele said previously, you can see how the execution is evolving for long executions. Okay, so do you have any question up until now? Okay.
In this case, when you dependency by the ISO, what happens if I have a really complex program where I use our functions and individual functions? So what happens if I don't start with the inheritance and so on? How much is the overhead and the
So the question is, what happens if you have a very large algorithm and you don't see the data dependencies? The answer here is that the PyCOMPSs programming model objective is to avoid you to worry about that. The idea is that you program your functions, you add your decorators, and let the PyCOMPSs runtime detect them automatically and deal with the data between nodes and all the stuff that is complicated. So our main objective is to keep you as much as possible not to have to deal with them. These examples are very simple so that you see what happens under the hood to understand the programming model. But at the end, the idea is that you have your application, and if it's well separated into functions, you can then decorate them and it should work under the hood as far as you decorate the functions and you add the comps weight on or the synchronizations needed. At this point, something that it's also to take into account is that here in this notebook, you see that I have synchronized C, but A and B are still there. So it's not necessary to synchronize something to invoke another function, another task, because at the end, you can invoke all of them and it will deal with the data automatically, seamlessly, and transparent to you. You only have to bring it to synchronize only the data that you want to play with in your main process. But the rest that of parameters that are necessary or transferred between tasks or required by tasks, they are automatically handled by the runtime. We will see larger algorithms afterwards. Yeah. So the question will be like, I'm just repeating for the people who is in the chat, how the live data of the task dependency graph seen. We are going to see that in a few notebooks because these one are very small and we cannot see that very quickly. But in the next one with, for example, a key means, we can see them. One can see it. Okay, let me see.
Well, Mustafa is asking about how some know about the available resources. But this is something that we will see in the
yes
execution environment.
Okay.
So wait until tomorrow.
Okay, let me answer here to the microphone. Okay. Okay, so I'm checking the chat where it is.
So if you scroll up, there are.
Okay.
Okay.
From the chat, Mustafa is asking how does COMPSs know about the available resources. This is something that we will see tomorrow, I guess, Jorge. This is something that we will see tomorrow because it's part of the configuration of COMPSs where you define the nodes that will be attached and how they are attached to the runtime. Valentina is, are there any restrictions on the types that are input and output to the task? Could I use a custom object? That's a very good question. The only limitation here with the parameters is that they must be serializable. They have to be pickled. So as far as you use any kind of object that can be pickled, it will be supported. And even for the objects that cannot be serialized, they could implement the set state and get state methods in order to define how they are going to be serialized and deserialized. With regard to the Python version I am using is 3.8, but we support from 3.5 and higher versions. Okay, so Javier Hernandez is asking, so could we remove the comps wait on and expect comps to solve the dependency? There are separate things. Dependencies are not handled with comps wait on. The dependencies are managed automatically. The comps wait on, it's only necessary to synchronize an object that has been produced or modified by a task. Fred is asking, the order for task definition matters? The answer will be no. The answer is no. What matters is the data dependencies between the tasks. Okay, so in order to ensure the validity of the execution, the runtime respects the data dependencies. And Germán is asking, what would happen if we update the variable A after the statement A? What A will be considered? If you update the variable, it depends if you have synchronized or you don't have synchronized that variable. If you modify A after the B statement and you shadow the content of A, the next task will consider the new value. But if you want to modify the real value produced by the second task, you will have to synchronize it and then modify it. So at the end, it will be considered the latest version of the value. Okay. Is there any other question? Okay. Okay, so let's continue. Okay, so let me start the runtime again. I will repeat myself a few times because I have a few notebooks. Sorry about that. Okay. One of the things that we have that has been asked is that what kind of objects can be used. I have said that they have to be serializable, okay? But you can also define your own objects containing task definitions. If you declare a class, so just to give a good starting point, any function that you define in your Python code can be declared as a task. No matters if it's a function defined at a module level or if it's a function defined within a class. The only restriction here is that since we are in a Jupyter notebook, it has to be declared in a separate file. But this is just a limitation of being within a Jupyter notebook because it has to be imported from the worker to be executed. Okay. This example gives a little bit more information about the task decorator. And I want you to focus in this import, which says from PyCOMPSs API.parameter import in. The tasks, as I said, they have inputs and they have outputs. Okay. The inputs are the parameters declared and the outputs are the returns. However, in some cases, you may want to define that the task has a parameter that it's going to be, for example, input only, or it's going to be a modifier of the parameter. For those cases, we have these directions, which can be in, or for example, in out, or even they can be out. It's in the documentation, but they can be used to define that a parameter it's going to have this direction. Focus in the last function, in the last task definition. I am saying that target direction is in. Okay, this is a special case where we want to say that self it's going to be input only. This is important for the runtime because you can say that a parameter has a specific direction, and then the task dependency graph can be even optimized for that cases. Imagine that you are invoking a task and it has an input-output parameter. So the task dependency graph that will be built, since it has an input-output parameter, it will be like a chain. So we are not going to gain any parallelism, but the result will be valid. Okay. However, if we don't want to have that or have that issue, we can define, for example, in classes that the target direction is in, and it will be break. In which case is important this, for example, or useful, let's say. For example, this info shape function, it's only doing a print. And self, by definition, in Python, it's modifier. So the default direction, it's input-output. Let's see with an example how those dependencies are respected. So we see that we have in class shape, we have area, which doesn't have parameters, but has these attributes. It multiplies. The perimeter calculates all the perimeter, but they are all returns. Describe has, it's not a task. A scale size, it doesn't say anything, but it modifies self.x and self.y. While info shape, it's just a print. So if we run this class, it is declared, and then we import it. So we are going to create two shapes into a list, and we are going to compute all areas. What do you think it will happen if I run this loop, which calls for each shape, its area? Let's see the task. They are two different shapes. So if they are two different shapes, let me see what will happen. They are two different shapes, and I'm calling for each individual object a single task. The runtime will know that they are different objects and they have different tasks, so they can be executed in parallel. So at this point, we are calculating all areas completely in parallel. If instead we have 1,000 and we have 1,000 cores, all of them could be executed completely in parallel. And the code that we have just written here is the task decorator and not even a comps waiton. We are going to have the comps waiton now because we want to get all these values. Okay. So if we do the comps waiton for all objects, we get the areas. Okay. So this is a game of declaring the task, submitting them, and retrieving the data that we want. If we go for a little bit more complex algorithm, we are going to declare a new object. We are going to scale. This is going to modify rectangle. This is why here it's modifier. And then I am going to check the area. the dependency here will be like rectangle has been modified, and this area cannot be executed until this task has been executed. And I'm going to show you then in the task dependency graph. We can retrieve then the final result to check that it is valid. Okay, so we see no future objects here. And with the perimeters happens exactly the same, but we will compare that in a bit in the task dependency graph. I'm going to show you here. So this is what happened, which is a little bit more interesting. If I split the screen in two, here we see the blue ones are scale size. Scale size. No, blue are areas. So this is the first loop that has run these two completely in parallel. Then we had a COMPS weight on, which has been put very quickly and hasn't been drawn here. Then we have the scale size here, which is the white circle, and then the area here, which is again, but there's a data dependency among them, we pointed out. Then there has been a COMPS weight on here. Well, there have been two, but it's painted as only one. But at the very end, we have a loop that seems that it is calling the info shape, which is not a modifier, and it is calling the perimeter, and the runtime has detected that those tasks for those objects are completely independent and they can be executed totally in parallel. So you may be writing a very complex code that probably you don't see the data dependencies because you don't need to, but at the end, once you run it, then the runtime detects them automatically and respects them so that all the results are completely valid. Okay? Okay. So let's move. This is going to be very quickly. The next one, which is exactly the same as the previous one, but I want to point out something. There's a feature in Python, which is asterisk args, okay? And I want to remark this just to show that the powerful that PyCOMPS is, the power that is. No matter what you define your functions in Python, we support all of the all the function definitions, even the most complex one, which is to have a parameter with asterisk, which enables you to, which is a dynamic number of elements that you don't know at the moment of declaration, you know it when it is executed. This is even supported. So what I want to remark here is that even if you have a very complex function, not only the algorithm, you have a function with 20 parameters and asterisk args and so on, this is still supported, okay? And next, to end up with defining classes and objects, until now, I'm going to run this one because this is interesting. I want to talk a little bit about a specific type of objects that can be used as parameters. Until now, we have kept everything very simple. We have simple objects that are inputs of the tasks, and it retrieves some other objects that can be primitives or whatever. But there's a kind of object that can be defined in the task decorator and enables you to use this is exactly the same as the previous one, and enables you to use a specific or to manage some parameters in a specific way. This is when you play with lists of objects. A list is an object, okay? So if you invoke a function with a list is the object, okay? It will be serialized entirely and submitted to the task, okay? But what happens if in that list you have elements that then they are used individually for other tasks? The data dependencies of the inner elements of the list is not detected by default, okay? So that's why we have the collection concept, okay? This collection defines that my list here is going to be a list of elements, and I want the runtime to inspect inside the sub-elements for any def in order to detect the data dependencies that may exist with other tasks, okay? So if it is not defined, the task will be considered as a whole, as a single object. But if you give that hint to the runtime will inspect what happens inside. Yep. Yes, there's a reason. The main reason of having collections is that managing multiple elements, individual elements, has a higher cost than managing a single one. Let me explain myself. If you have a list of 1,000 very small elements, serializing that list is very fast. But if you want to serialize 1,000 of very small elements, you have 1,000 access to disk. So in some cases, it is worth it not to have the collection because you want to submit the whole object as a whole. But in some cases that, for example, in numerical algorithms where you play with slices, then it's good to have a collection because then you can grab just a single part of the list, and even though you have a slightly higher cost, you gain in programmability because then you are dealing with the elements transparently.
So my list can be a slice.
Yeah, you can have a very big list, and you can say this list is going to be my parameter for the task, and it is a collection. Okay, for example, it is an input-output collection. So the task is going to modify, and then you say, I want just the first row to go to another task, and it will detect that those elements are modified by another task, and it will detect the data dependency among them. Right? Yes, by default, the question is if there's a way to define a list of lists. Collection by default has the maximum depth. So it supports by default all of them. Although there's a way to limit for not to go very deep. By default, you can define then I think it's a couple millions of depth, which is okay. So this is the concept of collection. So again, with the directions, I just introduced the collection in out. Here we have a collection input. This is going to be like a consumer of the collection, is not going to modify that collection. Okay, it's going just to accumulate the value. We have another task that has a collection input and two collection input. It will do all the sums of those two. And we have a scale which has a collection input output. Okay. Let me just stop here and ask something. In Python, objects, the parameters for the functions can be modified by from the inside of the function. So by default, they are input-output. You can modify a list from within a function, and you don't have to return because the pointer is exactly the same. So by default, the input-outputs are normally the rule, but the in allows you to break that and achieve higher parallelism. This is something that seems a little bit complicated when you are starting, but whenever you see the task dependency graph and you see the code, then with a little bit of analysis, then is where we detect the potential parts of the code that can benefit from this. So this is a loop that we used to do with an iterative method that we do with larger algorithms, that we do a first parallelism that we think it's going to work, but then we check the data dependency graph and we detect if there's, for example, a very long pipeline, that what's happening here. There's a dependency which is very, very strict, and it has a critical path which is very high. And then we loop over the code to see if there are potential ways to change slightly, a little bit the code to achieve higher parallelism. But the idea is that for simple codes, or even for larger codes, if they are well written, by defining the tasks and the COMPS weight on, they should work out of the box. Yep.
On the PyCOMPs you mentioned very early on, you said though there is no PyCOMPs in the function definitions, you need the PyCOMPs to the time. Is that to improve?
Yes, in this case, in this example is to achieve a higher parallelism. So in this case, we have the collection in here because we are going to share the objects and we want to achieve a little bit. Okay. Yes. With regard to the returns, there are a few ways. There are 3 ways, in fact, to define what it is going to be returned by a task. Here you see returns integer, but here you see returns 2. Okay. And even you could say nothing. Okay. These are the 3 types to define that there are going to be returns. The first one, with the returns and the type, it's a little bit anti-Python, because Python is not typed, or was not typed until we have Python typing. And it was how it was created on the very beginning. If you say it's going to return an integer, the runtime knows that it's going to be an integer, and it can apply some optimizations to retrieve that object. However, you can change that int with 1. It's going to return 1 element, 1 object, okay? No matter what, it's going to return just 1 element. So it will be like case 2. But here you see returns 2. It is returning 2 elements because it is returning here with a comma, sum and sum2. And we want to keep them separated. So they will be written in 2 separate files, and they will be able to be executed. They will be able to deal with them independently if some other task requires it. Let's see here how it is invoked, because this is add all C2. If I create a few shapes, I can create all these areas. Now, if I move to the monitor, and I go to the current task graph, okay, this has been executed very fast. I can wait for all of them, but here you see the task is called add all C2. Let me go to the okay, to the question of how the task is running. And this has been very fast. Let me go directly to the place. Here. Here, add all C2, it's returning two elements. It can be written like this way, or it can be written like this way. Okay, so this will be one of the returns, and this will be the second. So we have two future objects, let's say. So if you say that it's going to return one element, it will be returned like a tuple with a single object, like the example, the same way that I told before. If it's just a single object, it will be whole. If you say that it's returning two elements, then we have two, and then it will be able to play with them in separate tasks and with different data dependencies. Because the question is, if it's a list, why I have to say that it's two elements? Okay, because the returns in Python, they are always only one element, which is a tuple. Yes, it's even though it's not written with parentheses, it's always one element, but in reality, it's handled as two because with the equal, it is unrolling and assigning each element to each separate variable. Okay, so that's why we need that value then. So let me see if I can quickly go to the monitor. Here, the question before about what's happening during the execution, this takes a little bit more, and we see here the number of tasks running and executed. It has been very, very fast. I'm sorry about that. But having the monitor open and running a cell, let me run it again. Sorry. It is saying the tasks that are running and the ones that are pending and the ones that are running. If you give a higher refresh rate, then you will see with more refresh, but this is one second. So if I go and I stop the runtime, this has been, as you see, I've been invoking tasks and so on, and I haven't been taking care of the dependencies that they exist among the parameters. And now, once stopped, if I go to the complete task graph, then we see that this is becoming a little bit more and more interesting here. Okay. I want you to note at this point that the wider the graph, the more tasks that are completely independent, the better performance you are going to potentially achieve. Because if you have high number of resources, then the runtime will be able to offload all the tasks independently. Okay, so now just to remark this, the objective is to keep it simple, to define your tasks, try not to worry too much about the data dependencies because the runtime has to do it transparently to the user, and run it potentially in as many resources as available. Okay, is there any question?
How do we run the code and the design of Python dependencies to a better parallel?
You mean to define
Define function, and how can I define the object? There's some, I think that in this graph there's some bottlenecks. Like
yes.
You just suddenly stop,
Yeah.
And then you see.
Okay, you are asking why there are these bottlenecks here. Avoid them. That's a very good question. That's a very good question. In this example, there's how to avoid these bottlenecks that appear in this data dependency graph is the question. So this is what happens. Whenever you have in your code a COMPS wait on, a synchronization point, like here in the code, like for example, I have multiple cells that have COMPS wait on. For example, here, and then a little bit later here. What happens with COMPS wait on is that it blocks the execution until the next until the data that you are waiting for it's produced and brought, and the code that it is after that it's not being executed. Or the tasks that are defined afterwards, they are not submitted. Yes, in this case, the COMPS wait on it's acting as the point, the synchronization point, and it is not allowing for the next tasks to be executed. Okay, because they are not submitted to the runtime yet. So let me explain a little bit. Imagine that you have a sequential code and you submit a set of tasks. Okay, you invoke functions, and then you have a COMPS wait on. The COMPS wait on will stop there. The execution will stop there until that data that you are waiting for is produced. Okay, and then when that data is produced potentially in another node, then it is retrieved and the execution of the main code continues, and then the code can submit more tasks. So that's why a COMPS wait on is drawn as an element that synchronizes everything here. So the less COMPS wait on that you have in your code, you potentially will achieve more parallelism. And we will see here. No, it's fine. It's fine. So we will see a couple examples that they don't have a COMPS wait on until the very end. For example, in numerical algorithms, and they build extremely big task dependencies. So is there any question in the chat?
There is a question about the types of the return.
The types of the return. Well, the type is not mandatory.
When you have a list, you don't put the type.
No,
You put the number.
you just put the number. When you have a list, you just
And
need
you
to put the number.
a list of types. Or not.
Yes. Something that it is also supported is if you say, for example, let me write it down here directly. You can say, instead of 2, you can say that I'm going to return integer. This is also supported, but it is more verbose and probably anti-Pythonic. It is a little bit. Which is more interesting nowadays is if you define it with type hinting, like this. And this is also supported. This is more natural with the latest versions of Python. Okay.
You mean that the declaration, fast will take the typing from Python into here?
Yes, it works in all those cases. So we are still supporting the latest, the old way of defining the returns and the new ones. So if you define it this way with Python typing, it will also be supported.
But if the typing of the class functional is complex, and for instance, you define it with union, it takes it into account as well. No problem.
Yes.
Great.
Yes. Because at the end, it's just a number. So even with complex return elements, it is supported because it is static. Yeah.
It's further steps of maybe it's not very related, but something that came into my mind. it's imagine that you run in BCC and you know that task is supported, so you parallelize all your code and you put all your task comments, and then you have to run somewhere else where it's not supported. Then it's like an easy way to activate and deactivate tasks, so you don't have to modify all your project.
What do you mean that you can write or you cannot write?
So if you're parallelizing your code, and then that was because PACOMPSs is
Serializing the data?
and then you parallelize your code, and then you have to run these in somewhere else where PACOMPS supported. Is there an easy way to activate and deactivate without changing all your?
Yes, that's a good question also as well. The question is, what happens if I have my application with the decorators and I don't want, or I want to run it in a place where PyCOMPS is not available? Yeah. There's an easy way to deal with that, because some environments, we agree, not in all supercomputers PyCOMPS is available. And what happens? What we usually do in those cases is we create a dummy task decorator that it is available in our repository, so that you can grab that piece of code, you can include it in your project, and that dummy decorator detects if the application is being run within PyCOMPS. Then it works as a task decorator. And whenever you run it directly with Python, then the Python directly, then it will run the code like in sequential code, like if nothing is there. So the way that we usually do that is grab the dummy decorators that we have in our repository, add it to the project, and then that's it.
And is this done somewhere to be checked?
Yeah, I can tell you where they are, and I can show you exactly how to use them in the command line, because they are for that purpose. In this tutorial, we are focusing in Jupyter notebooks, and in tomorrow's session with the supercomputers, we will see in a command line in a supercomputer. That will be a good point if we want to play a little bit and see what happens and show you what happens.
Thanks.
Is there any other question? So I'm going to be very quickly with the 3 more notebooks, which are just extensions. Okay, so until now we have tasks, synchronization, and we have added the concept of directions and collections. Okay, so what happens if your application deals with files? Okay, so objects are very good, are very nice, but not all applications deal only with objects. Some of the applications need and require files. For that purpose, PyCOMPS is enabled with another label, which is file. Here you see, with the direction of the file. Okay. This label, let me run this notebook. This label is intended to be placed on the task decorator to define that a parameter is of type file and its direction. For example, let's say this first task. This first task has 2 parameters. One is content, which is a regular object, and fout, which is going to be a file out. Okay, so we know from the content of this function that this function is taking this file and it's writing content on it. So this is a producer of a file. Okay, so with this annotation, the COMPS runtime knows that it is going to produce a file. and it will automatically and seamlessly deal with that file, and it will move it across the tasks that require it. The next one, it's another one that as an extension of the direction and the file, which is going to receive a file, it's going to open it and append some content to it. So this is a modifier task. The first one is a generator, the second is a producer, and the third one, which is read file, it has a file in, because it's only going to read it and close it. Okay, so with this very small annotation, you can tune your application that it's working with files, and the runtime knows that they are actually files and will transfer them across the nodes. This is very important because it allows you to run the same code in different environments, and the runtime will deal with the files without you to have to place the files in a single place or whatever. It will deal with the versions and the files that are required. And how they are invoked? Exactly the same. You don't have to define a specific object. They are just strings that point out to a specific file, and the runtime knows that they are files and they are transferred. Okay. However, there's one key here, is that since they are files, they have a specific function for their synchronization, which is the COMPS open, which retrieves the file and opens for you. So it is exactly the same operation as a regular open for files. Okay, but this one is enhanced to retrieve the file from the task that has produced it and open it for you. Okay, so any question with regard to files?
You didn't do this special type of open and do a regular open, Python would not find that.
Exactly. If you do a regular object, a regular open, Python will not find the file, because comps open is retrieving the file and opening it.
This file, in this case, has to be, can be a file that's localized, serialized in a particular place, or does that have to be distributed, or
No,
anything?
it has to be in the well, it can be anywhere, but it has to be mainly in the place where the application is being run. And the runtime has some enhancements to detect if that file is in a shared directory, or if he has to transfer because it is not in a shared directory.
Okay, but the coder doesn't have to use whether it's shared or not.
No.
Volume.
No.
The developer is the idea that COMPS is like you have a cluster in your machine, so you program as you were in this machine. So if you put the path, if you don't put your entries, will be a path in this machine, and the runtime will copy the data to the other machine where the task is executed. But from the programming point of view, it has the view of only one piece and one memory without dealing with the distribution.
Yes. Okay, so moving forward, I'm going to talk a little bit of the two latest, two last things of this session, which are related to the task definition. As you may see, the task declaration is done with decorators, but they are not the only ones in our ecosystem. We have a few more decorators to tune the tasks, or to give more information for the task to make them more rich and to have more features. In this course, we are only going to show you, or in this session, I'm going to show you just two more, just to give more like the last bits for the syntaxes. But there are a lot of them that you will find out in the documentation. And the most important ones, apart from the task decorators, are the constraint decorator, which allows you to define specific requirements for the task. For example, in this example, we are going to define that this task requires 2 cores. So there are codes that you can declare within a function that may be using some kind of internal parallelism, like, for example, if you are using NumPy, or if you are using a specific library that has internal parallelism. So you can tune and say, hey, this task is going to use multiple cores, or even it requires 20 gigabytes of memory, or any kind of other requirement that you may imagine that it is supported by the runtime. Okay. What this does is to notify the runtime that this task has specific requirements, and the runtime will respect them. Okay. So, for example, in my machine, I have 4 cores. If I have this square task and I submit more of them, the runtime will know that since I have 4 cores, it will be able to run only 2 at the same time, because each one is using 2 cores. Okay. And if you have multiple tasks with different constraints, the runtime will respect them all as possible. Okay. Yes. Yes. There's a yes. It is there's a configuration file that will be shown tomorrow, where you define how the environment is, how many cores, how many nodes, and these kind of things that are explicitly defined there. And from that amount of available resources, the constraints are a part of them. And finally, to end up with this session, I'm going just to show like another decorator, which is the @implements, which goes in conjunction with the @constraint, which enables you to define multiple implementations for a task. Okay, this is the most advanced thing that we are going to see in this session. For example, imagine that you define a task that is doing a very complex algorithm using NumPy. Okay, but you want also to have a task that does exactly the same but with GPUs. Okay, so that will be two tasks that are doing the same, but they depend on different constraints. Okay, one requires a GPU and the other one is not. If you, as developer, provides COMPS with multiple implementations for the same thing with different constraints, and you identify it with @implement, what the COMPS runtime will do is it will see what resources do I have available. And if the runtime, if you are running your application with PyCOMPS in a cluster with GPUs, it will try to run the most efficient one. Okay, so this allows us to the runtime to choose which version to use. And you can have a single code that can run in multiple infrastructures, maximizing the usage of the available resources. Then if your code is moved to another cluster where it doesn't have GPUs, then the COMPS runtime will select the base task, which is only using NumPy, for example. But then if you move your code to another which has GPUs, then it will try to run as this. The COMPS runtime keeps track of the execution of the tasks. And this execution of the tasks, the COMPS runtime know how long they are taking. So this is also taking into account to select which one is going to be more efficient. So just to end up with this, the @implements decorator allows you to declare for the same task multiple implementations with different constraints. Okay, is there any question? Is there any question in the chat? Okay, so with this, I end up my presentation and it's time for a break.
There is,
Oh, there's a question. Are there any interdependencies with other decorators? I don't understand this question. Interdependencies with other decorators. Do you mean LRU cache? Okay, I see. The PyCOMPSs decorators are by design isolated from other decorators so that you can use them. However, the position of the Python decorators is important. If it's below the task decorator, it will be executed within the worker, so it can be catched in the worker node. But if it's placed on top of the task decorator, it will be run in the master node or in the main node where the code is run. So the question is, they are compatible, but the place matters. The placing of the decorators is important. What he was asking is this. You have a task and you have your own decorator, for example, or there's a Python decorator for cache, which is. So if you say this, I think this is, I don't know the syntax, but I think it's something like this. This will work. It's your decorator, and the PyCOMPSs decorators are designed to be isolated from other decorators that even they are not belong to the PyCOMPSs ecosystem. However, if they are placed below the task decorator, this will be executed within the task. So it will be part of the computing unit. So it will be executed in the remote work. However, if this decorator is placed here, this will be part of the main code, and it will be executed before the application is submitted. Okay, so this is the only concern that has to be taken into account if you want to join your own decorators with the PyCOMPSs decorators. Okay, hello and welcome back to this programming distributed computing platforms with COMPSs tutorial. In this third session, we are going to deliver like the Python hands-on with Jupyter notebooks. So the idea in this session is that all of you can play a little bit with PyCOMPSs and see what you can do with it. Of course, if you have any issue, let us know in the chat or let us know, because there are some team members around and in the group that can help you to solve the issues that may happen. Okay, so the first thing to start with the hands-on is with regard to the instructions that you have received, probably. Let us know if you haven't received. And there are two ways to do this hands-on. One is with a virtual machine that we, and you should have downloaded before because it's a couple of gigabytes. This is recommended for people using Windows, or even if you want to have it in a isolated environment with VirtualBox. And the rest of the instructions are exactly the same if you are using Linux or Mac or the virtual machine. Okay, so for the ones who are going to use the virtual machine, open VirtualBox, start the virtual machine, and those are the user and password to log in. And once you are logged in, open a console and you will be synchronized with everybody else which are going to use directly the PyCOMPSs CLI. Okay, so these are the instructions and many of you have already done them. Have you installed the PyCOMPSs CLI? Do you have any issue? I know that some of you have some issues, so we are managing to solve them. Okay, so once you have the PyCOMPSs CLI, go to one folder and do the git clone and clone the tutorial apps repository.
The question is, why do you have us install with sudo?
Oh, it's just a recommendation for because it adds the binary, the link to the invocation automatically. If you install it with sudo, it will install in your home folder, and in some distributions the .local/bin is not automatically in the path. Just so you know. So you can choose. If you install without sudo, take into account that you should add the bin to the path. Once you have the repository cloned, I am going to continue. I'm going to go step by step, following you, so you can follow me, command per command. Okay. So do you have the repository already cloned? The PyCOMPSs CLI is intended to work in your own terminal because it will download it uses the Docker container that you have pulled to run everything inside. So I think it's better if I it's better if I explain myself. Okay, so the question was how to run these commands. Okay. So I have already cloned the repository in this folder. Okay, and I move inside the repository. Okay, so the next step is to use the PyCOMPSs CLI, which is a tool, which if you check PyCOMPSs-H, it's a tool that we have designed to give a friendly command line interface in order to run PyCOMPSs applications. Yeah, he will. Okay. So once you have the repository clone and PyCOMPSs CLI installed, the next command that you have to run is Okay, so the first command that you should write is PyCOMPSs init -n Docker tutorial and -i comps/comps tutorial 3.1. This will, oh, sorry, I'm going to paste it into the chat. Oh, sorry. This will start the container that you pulled from the instructions. Oh, what I've done wrong. Oh, sorry. Docker tutorial, Docker. My fault. Germán Navarro is asking, how can we get the PyCOMPs if we are not using the VirtualBox image? The PyCOMPs is self-contained within the Docker image that we have provided and you should have pulled. The PyCOMPs CLI is just a command line that deploys the container and you can use the PyCOMPs installation which is within it. Okay, so have you already initialized the environment? Navegador? If it doesn't open the browser, copy the URL and open that explicitly that URL.
No, you have to install Docker.
Oh.
We need the Python.
Oh. See, you need, for those of you that are having issues with Docker, pip install Docker. Sorry, just 1 second. Okay. Yes. So the next step, I see many people that has already initialized the environment. The next step is to start the monitor. And for that, you have to write PyCOMPS monitor start. Okay? It will give you an URL at the end, like this one, that you can open in your browser. And you will see this window, okay? You have to log in with root, okay? Because this monitor is running within the container, okay? So you just write root and it will open. Since the container is clean, there hasn't been any execution, there are no applications here to see. But keep in mind that keep this browser somewhere because you will be able to check it afterwards. So
Always you will put forwards when you run things.
Mm.
You will push forwards.
No. This root is only for when you are running within this container. Imagine that you have PyCOMPs installed in your machine. You should write the username that you are logged in. This is just for because it is running within the container. Your username, exactly. Because all the information from the monitor is stored in a hidden folder in your home, and you will find out there everything. So it's the way to keep things secure. The next command, have you already started the monitor? Okay. The next command is PyCOMPSs Jupyter. And this will start Jupyter Notebook within the container, like in the same way as the monitor. So it is starting a Jupyter Notebook inside the container where the PyCOMPSs installation and everything is. So from this point forward, everything that we do is inside the container. It is isolated and we are not dealing with the machine anymore. So just pick the URL, go to your browser. For example, here that I have the monitor, I paste it, and you should see if you have done it within the tutorial apps repository, you should see exactly like the same as me. Well, I have 2 files, extra file one. Let me know when you reach this point.
There is 2 questions in the chat.
Okay, let me see the questions.
One is about invalid choice Docker tutorial with PyCOMPSs in it. I don't know. And then another one about in the VM.
Federico Broghi has written that he has an error with the argument. Federico, you please check the PyCOMPSs init command, because I guess that you are swapping some of the parameters. The command that you should run is, I'm going to repaste it again. Fred is asking, data are lost are Docker pull, or there is a Docker volume setup? Everything is contained within the container itself. So if we remove the container, all tutorial data will be lost. When I start the monitor, the browser opens in the URL, but nothing is listening in this port. Heribert, I guess that you missed running PyCOMPSs monitor start. You should run PyCOMPSs monitor start. It will start the monitor, so you can open the web page and then open Jupyter. Okay, so now that it seems that most of us are in a safe step where they have Jupyter running, we are going to continue running, and you are going to play directly with PyCOMPSs. Okay, so if you go to the folder called Python, here we have a set of applications written in PyCOMPSs, written in Python parallelized with PyCOMPSs, and inside there's a folder called Notebooks. Okay, do you follow me? Okay. Inside this folder, you will find 3 main folders. Within syntax, you will find all the exercises that I have shown in previous session, if you want to recap or something like that, okay? But now, in this session, we are going to move to the hands-on folder, okay? And now, let's run the first notebook, which is called 8 sort by key. Okay, so now in this session, what we want you to do is to run real applications parallelized with PyCOMPSs so that you can see the syntax and how they are parallelized, and feel what happens when you run it in your machine. Before running it, I want you to know that the container that you have developed, it's configured by default with 4 computing units, so it is able to run up to 4 tasks at the same time with the amount of memory that you have, Okay, so by default it will be able to execute 4. Okay, so this very first application, it's not like the toy examples in the previous session. It's a real application that what does is to sort a set of files, the contents of the elements in those files in a specific order. So it's a very simple case that mixes files, objects, and a couple loops. So first, follow me clicking in the run button, okay? Follow me. If we run the first one, we are instantiating a function that is going to generate a dummy dataset to run this application, okay? So now in the next one, we are going to set how many files and how many pairs we want to create that dataset. The larger, the larger files it will create, okay? So it's just an example. It's going to create, for example, let's say we want 4 files, and let's say that we want 10 pairs on each file, something really small, okay? So if you run it, it says that it has created these data files, okay? We can check them with the next cell, and they are really, really small, okay? Now that we have a data set already created, let's start with what we said that this is the first point with Jupyter Notebooks and PyCOMPSs. Let's start the runtime. So we import PyCOMPSs Interactive as PyCOMPSs, and then start the runtime. At this point, you should get the log path and this line of asterisk once the runtime is up and running. Is it okay? And now, as we saw in previous session, we import the task decorator and the file input because it's the one that we are going to use, and we are going to declare a couple of tasks which are going to do our sorting. The first one is sort partition, which consumes a parameter, which is data file, which is an input file. So we are intended to have a task that reads one file, gets its content, and sorts it, okay? It returns a list, one single element, with the contents of one file sorted. And then we have a second task, which is able to merge, reduce, or join 2 partial results from 2 files. Okay, so we have done one task which is able to read one file, get the results and sort it, and another one which is able to merge the contents of 2 files. Then we have an auxiliary function which runs over the files, over the objects to do the reduction. And finally, we have our main application. This application imports the COMPS wait-on because we are going to synchronize the final result. And what it does is, first, we have a first loop which iterates over the files and appends it to a list so that we have all files in a list. It starts a timer, grabs the time that it's currently, and then for each file in our dataset, it calls the sort partition task or function, which is decorated as task, and appends the result into partial sorted, which is a list. And then with that list of partial sorted elements, invokes the auxiliary function merge reduce, which loops over all elements calling to reduce task in order to achieve the final result. If you run this cell, like me, it will take a few seconds and it will give you the elapsed time and the final result. Okay? Next, stop the runtime. because once you stop the runtime, it consolidates the task dependency graph. And now it is when we go to the monitor, we click in refresh here. Now it seems that interactive one has appeared because this is the first time that we run. If you click in interactive, and then you are ready to see what happened under the hood after the execution, because this one has been very fast. If you click in task information, it says that he has detected 2 tasks, sort, partition, and reduce task, and it says how many of them have been executed, 4 and 3. And if you go to complete task graph, you see the task dependency graph that has been generated. Okay, so this is the very, very basic example of an application that has been parallelized in the most simple way. Okay, were you able to run this first application? Okay, so now let's move to a larger one, because this one is very small and well, you can, then you feel how it is parallelizing with PyCOMPs. And now we can go to a more complex one. The next one is the 9 K-means, which is another application that we want you to follow the execution that has a peculiarity. This notebook is a notebook that contains the K-means clustering algorithm that has been parallelized with PyCOMPs. If you take a look at it, you will see that it's much longer than previous notebooks. So it's a complete numerical algorithm with more features that enhance its execution. For example, if you follow me and you start the runtime, I will keep you describing how the algorithm works. The K-means works trying to look for the closest centers to a cloud of points, okay, for a given number of clusters. So again, we import the task decorator. In this case, we are going to import NumPy because we are going to use some of the NumPy features. And then we start declaring the functions that we are going to use. Here, we see that there's a one generate fragment function whose decorator has been commented out because we want to have the points, the data set in the main memory of the notebook because we want to plot them, but it is not mandatory. In this case, just for plotting purposes, it's not going to be declared as a task, but it could be. Then we are going to declare another task that calculates the distances from each center to a set of points. Then another task that calculates the accumulated distances between those points to the centers. And then again, we need another reduction function to reduce the centers distances and a merge reduce auxiliary function. What this merge reduces does is to take 2 by 2 from the results given in data list and goes merges like in an inverted tree fashion. Finally, in order for the algorithm to work, since it is an iterative algorithm, we need a function that checks the convergence to see if the centers have a distance less than a given epsilon, a given distance. Then we instantiate it. And finally, we have another function which plots the results achieved from the K-means execution. So this is a real application that has been taken. We have added the decorators and we are going to run it. The next cell, which is previous to the stop, is a little bit particular. In here, you see that it imports the IPy widgets and it plots in line. Jupyter Notebooks enables you to define applications like in the way that you are going to run and you want to present them. And this is a special case that we join everything together, the power of Jupyter Notebooks and the power of Python and the parallelization of PyCOMPs. So if you run this cell, what it will create is a set of buttons to configure the k-means, which will be the number of points, the dimensions, the centers, and blah, blah, blah. All the parameters to for the k-means input. The k-means is an iterative algorithm, and it starts first creating a random point, then iterates while it hasn't converged. It iterates, checking the convergence, running cluster point partial function for each fragment, then the partial sum for each fragment as well, and then reduces the partial results. Okay, and then there's a COMPS weighton here, which grabs the result of the reduction in order to check the convergence, which is checking here. So you see here that it is launching a set of tasks, it is submitting a set of tasks, cluster point partial per fragment, partial sum, and all the reduction, and then it waits. Once it checks it has converged, iterates again, submits the next, for the next iteration, the tasks. So this is one of those cases that was said before, that what happens if COMPS weighton stops the execution, okay? But in this particular case, we cannot avoid the COMPS weighton because we need that value to break the convergence. It's not the same if we break in the fifth iteration or in the 10th. So if you run this cell, it will appear a fancy let's say form where you can tune the parameters and you can run it as many times as you want. I am going to click it with the default values and I'm going to move to the monitor so that you can see it running, or better, I'm going to split the monitor here into two so that you can see while it is running. Once the runtime is running, you can refresh and it will appear here, the application. So you can go to current task graph and run it. It will start running. And you may see here that the tasks are appearing, being pending. Some of them are running. And depending on the refresh rate, you will see it more faster or slower. Okay, here you see we have caught a piece of a whole iteration. At the end of the execution, it plots the result that has achieved on the 14th iteration. Okay, with the result, so it has achieved the stack. And if we stop the runtime, then it will consolidate the task dependency graph, and you can go to the COMPS monitor again. Once it finishes, now it has finished, you can go to the complete task graph, and you will see a real use case task dependency graph that per iteration you see the tasks that have been executed. So here, if you zoom out, you will see the 14th iterations. Okay. Yeah, any question?
I have a question regarding the COMPS weighton.
Mm-hmm.
I was looking at it, and first you find clusters.
Mm-hmm.
which is calculated in a task.
Mhm,
And then you calculate partial result
mhm,
using the cluster's variable result.
mhm.
Then why here you don't have to do algorithm?
Mm,
So you find clusters, then you find partial result, and then you find mu. Then why do you have to wait for mu? And you don't have to wait for clusters, for example, because partial result uses clusters,
yes.
which wasn't a task.
So the question is why I have to wait for mu and not for partial results.
And not for clusters when you
Or
use
clusters.
yeah.
Yes. This is the cool thing of PyCOMPSs. The cool thing is that you are using the objects as normally you would use them until you need to grab something explicitly. Okay, so clusters here at this point will be future objects. And they are the inputs for the partial sum, because here it's an input. So PyCOMPSs is automatically resolving the dependency that exists between the cluster point partial and partial sum task. And what it is happening is that under the hood, partial sum cannot be executed until the cluster point partial that produces that data is not executed. And when it finishes, the runtime automatically transfers that data from one worker to the one that partial sum is executed automatically. So what it is doing, it is moving the data between workers when needed. And the only moment that you need to grab something from the workers is when you have to check something. And in this algorithm, it's only the distance to the centers.
So if you did a function that does this check, then you wouldn't need to wait because the Python would understand that it has to wait for the.
You mean for the mu?
Yes.
The mu is mandatory in this one because it's a future object. It's the result of the reduction.
Yeah, but you would create a function that it only.
Yes,
check.
exactly. But the thing is that if you create a function that gets mu, you will be able to do something with that function, but it will be still in a worker side. And we are trying to break the loop in the main code. What you're saying is totally right. That if you want to do something else with mu in another task, you won't need const waiton. The only necessity here for having that const waiton is because we need that value to break this while loop. Okay?
I can't get with a monitor, I can't get
The task dependency graph?
the task for this one, for the previous one, for the small key.
Yes.
Fine, but I can run everything.
Have you stopped comps here with the latest? Have you stopped comps before going to the complete graph? You have to stop comps. Otherwise, the complete graph won't be generated and you cannot check it out.
It tells me the runtime is not running. Funny thing.
Yeah, if that happens, for those of you that have any issue and says error like the runtime is not running, what you have to do is to go click on kernel, or this is kind of what happens or what to do if something fails. Click on kernel and click on restart and clear output. Okay. Once you do this, it will clean up everything and you will be able to go to the beginning of the notebook and start running again. Okay. For those of you who are interested in the k-means or may seem like, there's another notebook which is 9 k-means reduced chunks, where it is exactly the same as the previous one, but has one extension or one difference, let's say. In this notebook, what it is doing is we have changed the reduction function, and instead of merging 2 by 2, it has a defined arity. Let's say that you want to merge, instead of 2 by A and B, you want to merge 4 at the same time, or 50 at the same time. This is a case that sometimes makes sense if you want to merge all tasks that are executed within a single node in just a single task, that you can control the arity of the reduction, okay? And what I want to point out here is that at the end, you as a developer is the one who has the full control over the algorithm itself. In the way that you define the reduction, it will be executed. So, and then we come back to what we said in the previous session. You run your application, you get the task dependency graph or the trace file that we will see later on. We detect a bottleneck or an issue or something that could work faster because of its missing parallelism, it's going slow for any reason, and then we iterate over the code to see what can be done in other way to make it better. Okay, another hint here if you're using Jupyter Notebook. As you see, the ones that I have already opened appear in green. My suggestion is, instead of continue opening more than 3 or 4, I suggest you to select them and shoot them down, okay? By this way, you will free some CPU and the next notebooks will be a little bit faster. Any question until now?
Okay.
Hmm?
Rerun everything. Or the program.
It's broken?
No, it's stuck on the code.
Let me see. Check it out. Okay, so let's move on to the last notebook that will be guided, which is a 10 Cholesky. If you open the number 10th notebook, Cholesky, this notebook contains the Cholesky implementation which give you the symmetric positive definite matrix A as a result from the upper triangular U, such that this rule is followed. This is an algorithm that may seem simple on the implementation, but that has an internal parallelism very interesting. Okay, so if you follow me running this exercise, you will have the runtime running. Here, note that in my case is interactive 3, so it will appear in the monitor as interactive 3. Then we import the libraries that we need, and we instantiate the task definition needed. As a difference from other notebooks, you will see that all of them are in the same cell. You can do both things. You can define your task in individual notebook cells, or you can define more than one in a single cell. So we have one for creating a random block, and we have the common functions that we will find in any Cholesky: odd RF, soft triangular, and gem. And now we need an auxiliary function to generate the data set and the main Cholesky algorithm, which is doing it's working with blocks. And then we have the main code. Again, as in the k-means, it has some widgets that allow you to tune the execution. Okay. If we run with the default values, it will take a matrix size of 8 blocks per 8 blocks, each block being of 1024 per 1024 elements. So it's an 8000 per 8000 matrix. If you run it, it will take a few seconds. In this way, it will find the task. It will do all its magic under the hood. In my case, it has taken for the initialization 4.5 seconds, for the decomposition 10 seconds, and the total time 15 seconds. Okay. Let's stop the runtime now, because I want to show you something here. If we go back while it is stopping to the Cholesky block algorithm function, you will see that there's an outer loop, an inner loop, and 2 more loops here. And there's no comps wait on this algorithm. This algorithm is very grateful because it's very fancy, because there's no need to do a comps wait on within the iteration. And this is one of those cases that can be done without stopping, like in as contrary as on the k-means. And this case is particular because it works very well. When you get the result, then you can retrieve and do the comps wait on for retrieving the final result. And for example, in this case, we didn't want to do the comps wait on and retrieve the result. We just wanted to measure time. If we want to measure time and we don't want to retrieve the result, we have the comps barrier function, which is only for stopping and waiting for all submitted tasks to finish, and then we can measure times safely. Okay, so there's another function to the list. Once it has finished and the runtime is stopped, if you go to the monitor, refresh, and go to the complete task graph, it's a good point to see how powerful PyCOMPs can become with just adding the decorators to an algorithm that it's by definition good. And this is the task dependency graph that PyCOMPs has been able to extract automatically from the algorithm. Okay, with even a small example. And PyCOMPs and the COMPS runtime will respect all these data dependencies, and it will execute everything as parallel as possible in the available resources.
So in this case, for example, I mean, it looks like you're resetting the environment variable MKL now forever.
Mm-hmm.
Is there a way to get that from PyCOMPs? Because I mean, in reality, you're already defining the resources before somewhere in XML file or what you said. So there should, I mean, in my understanding, there should be a way of PyCOMPs setting this variable from outside or not. Because you're basically, I don't know, intruding into the process of PyCOMPs and setting, I don't know, your own relations.
The thing about MKL in this algorithm, the reason is that NumPy by default has internal parallelism if compiled with some libraries, but not only with MKL. It can also be compiled with BLAS, OpenBLAS, or whatever, and it can exploit internal parallelism. In this notebook, what we wanted is to make sure that it is not using internal parallelism, so forcing it not to use it, because that's why it is overwritten to 1. In other cases that you want to use inner parallelism, then it's depends on the user to define how that internal parallelism is going to be, like, for example, if you have NumPy compiled with OpenBlast, you will need another environment variable, another different one, which is OpenBlast num threads, I guess it was. And then,
What I'm kind of trying to say is potentially dangerous because I mean sometimes you're not aware which algorithm in NumPy or something is internally using parallelism.
yes,
So it can potentially, I mean, from my understanding, it could potentially, I don't know, a couple of resource management of PyCom because it's internally starting any processes that are not managed already.
that's a good question. And there are two things here about having internal parallelism and PyCOMPs. The first one is, if you select, if you set a constraint in the task with add constraint, we add automatically those variables to force to do that. But what happens if you don't do that? What happens if you don't do that is that the NumPy will try to exploit internal parallelism, but in how many resources? The thing here is that if there's no constraint set, the default is that each task consumes one core. And it is stick to one core. What will happen is that the internal parallelism, even though it is opening, it will have process affinity, and all those inner threads will be executed in the same CPU. So you won't get benefit from the inner parallelism. The only way to get benefit from the inner parallelism is to define a constraint with multiple cores. So
If you wouldn't set this environmental variable to one, it will still run in one.
yes,
Okay, okay.
yes, it will still run in the same way, but it is there to trigger this question.
Well, I was not sharing one. What would be the performance between computing this matrix via PyCOMPs and computing it on a more traditional way? And I'm answering that the expectation is that in parallel is going to be faster, but I'm not sure what Alberto meant by a more traditional way.
Yeah.
Then there is a question from Valentina: how can I install new packages into the Python environment?
Yes, exactly. Pip install. In the Jupyter notebook, if you want to install something in the Jupyter notebook, there's a magic keyword that allows you to run. But if you want to install something and you want it to stay, Valentina, if you want to install something, you can go here into Jupyter, you can go here, new, open a terminal, and everything you install here will be installed within the container, not in your machine, within the container itself. Okay, so
I was a bit confused by that question. So what you were saying about the environment
variable,
variable
Mhm.
is that even though you set another variable, you said two threads, that the definition would have been the same because you didn't define any constraint to that.
in this case, if you want to run with multiple threads inside a task, so NumPy uses multiple threads, you need that environment variable to be present and be used. In the latest versions of PyCOMPs, like the current, this is not necessary, because if you say here that I want a constraint of computing units equals 2, then it will take 2 cores inside. But the possibility of having the environment variable here allows you to play with inner and outer parallelism explicitly so that the user can play with it directly. So I guess we are running out of time because it's 1 o'clock. And for those of you who are interested or feel more interested on starting, we have prepared an exercise that it could be interesting so that you can play with it and challenge yourself to see if you have understand how to do that. And it is this one, 11 word count exercise. In this, you will find a word count algorithm, which is already written in Python, which is thought to have a first phase with a function which reads the files and counts the number of words there, and a second phase like merging, kind of like the first examples that we have seen, so that you can get insight from the other notebooks. So my challenge for you will be to take this notebook, which is in sequential, it's completely sequential and it has some functions to do that, and try to solve it and parallelize it with PyCOMPS. Maybe if you give it a quick look, somebody can tell me what would you do?
Maybe we can use some approach like sort key.
Yes, the sort by key is a fantastic approach to solve this. So the key here will be first to import the libraries. So very quickly and briefly, import PyCOMPS.interactive as ipycomps, and then ipycomps.start graph equals true and monitor equals 1000. Okay. In this way, we start the runtime. Now we need some imports to parallelize which are from PyCOMPS.api.task import task decorator, and from PyCOMPS.api.parameter import, we are going to need files because the input is in files. So we are going to need file in. It will also be accepted here to say import asterisk, and it will import all which is inside the parameter library. So file in, file out, file in, out. And now it's time to start decorating. So the decorator will be, for read file, will be like task. Does it return something? Yes, it returns a list. But we can say that it returns one element. And we have to define the type of file path. File path, it's file in. Okay, we have one. 2 left. Then there's a function called word count. It can also be a task because it grabs the result from the task that reads the data and counts the number of appearance of each word. So let's define it also as a task. Does it return something? Yes, returns equals 1. Do we have to define some of the arguments of the parameters? No. And finally, there's a function called merge two dictionaries. This one is also target as a function. So we have to decorate it. Task. Does it return something? Yes. Turns one element. Okay, now we are ready. But are we ready to run? What will happen if I run it? Take a look at this. If I run it, I said that the basis of the PyCOMPS is to declare the tasks and add any synchronization needed. Okay. So if I run the algorithm over the files, it will look over the data set. But if I try to print the result, do we have the result or it has been computed remotely? Remotely. If I run it, it will say, hey, error, it's a future. So we are missing the comps wait on. So in order to solve this, from pycomps.api.api import comps wait on. And then we will need here result equals comps wait on the result. And if we run it again, then it brings back the result and we can check the final result. Finally, but not less important, we have to stop the runtime. Don't forget this step. pycomps.stop. And now, if you have still the monitor, you can refresh and go and check what has happened in the complete task. And with this, finishes this session. It has taken more time than expected. Sorry for the inconveniences with the dependencies and the setup. We will try to improve it for the next tutorials. And hope you enjoyed developing your first application with PyCOMPs. Remember that in the repository, you have all the material here and in the syntax folder. The last step, and with this we finish the session completely, is how to stop safely the environment. First, you should close the tabs for the monitor and for the Jupyter notebook. Once those tabs are closed, then go to your terminal and with Control-C, stop the Jupyter notebook server. And now we can clean we can clean the Docker image with PyCOMPs. Well, so sorry, I forgot this to mention. PyCOMPs monitor stop first. PyCOMPs monitor stop. And then PyCOMPs remove Docker tutorial. This will remove the running container, but not the image. So if you do again the init, the PyCOMPs init, you will have a fresh instance of the container where you can play again with PyCOMPs. And that's it. Thank you for listening. Is there any final question or?
Okay, so good afternoon. We'll start now with this session on the dislib. So what is the dislib? It's a machine learning library which has an interface similar to scikit-learn. Some of you may know scikit-learn, no? But it's parallelized internally. Okay. So it has this unified interface based on the fit predict model. Okay. So you instantiate the model, you can train the model with the fit, and then you can predict. But internally, it uses a distributed data structure. It's called the DS array, where then the data can be in different memory nodes of a distributed platform. And this distributed platform can be a cluster, or can be a cloud, can be different environments. Okay, and then with this structure, what it enables is to first have the basis for parallelizing, because we can operate on the different blocks that compose this array. And also it enables to parallelize with tasks, okay, since we have then tasks that operate on each of the different blocks of the DS array. And in this case, the parallelism of PyCOMPs is hidden to the user. So you will be now in the hands-on using the dislib as user of machine learning, and the machine learning, the parallelism, sorry, will be transparent to you. I will tell you a bit more how it's parallelized, since in the morning you've been seeing how PyCOMPs work and all this. But for a new user that doesn't know anything about PyCOMPs, it can use the dislib in a transparent parallel. It's also open source. We have all the code, and it's open for contributions, for users, for feedback, etc. It offers multiple methods, and I will relate them a bit later in another slide, but it's not right now supporting directly neural networks. Okay, it's more the classical machine learning, like clustering methods, classification methods, model selection, etc. Okay. This is the structure of the DS array, the distributed array. So basically you have samples, no? And each of the samples will have multiple features. Okay. So this can be seen as a matrix, okay, organized in this way, where the rows are the samples and the columns are the different features of the data. And a block of the DS array will be a square, okay, a rectangle of this matrix. So we decompose the matrix in blocks, all of them in principle of the same size, except those in the corners, but we are going to imagine for simplicity that is perfectly having size multiple of the size of the block size, no? And then when we have divided the DS array in these blocks, the different methods operate on the blocks of this DS array. Okay? The difference is that then we don't need all the blocks to be all the time in the memory of the nodes. Okay, so how does PyCOMPs work? When you generate a task, as we have seen in the morning, the task eventually is scheduled for execution when the dependencies are free, and then the PyCOMPs will read the data. In principle, are serializing files, so we'll upload data in memory, do the operation, and then serialize again the output data into files. No? This is an overhead of reading from files, operating and writing, but it has as an advantage is that you don't need all the data in memory all the time. You only need in memory the data that is going to be operated the data that is going to be operated by the task. Okay, so what does it enable? It enables to have larger data sets that will be in the file system, and you only will have in memory the data that you need for operation. So this enables them to have the methods operating in very large data sets. If you think of a single node, this works, but in addition, you can use the memory of multiple nodes, okay, in a transparent way. The user don't know the amount of memory that is using, because if you use 8 nodes of Mare Nostrum, so you have the aggregated memory space of the 8 nodes available for your application. But for the application, it's like a sequential program, no? Because you are programming sequentially, just that is running in parallel. So you can use a larger memory spaces, but even you can have larger data sets due to this out-of-core mechanism that you upload the data in memory and you upload every time you need to operate. So this is one of the important fields. Then, well, you will see, we'll have in the demo that you have some methods for operating with the data, accessing rows or columns, slicing, etc. In following a similar syntax or the same syntax as the NumPy arrays, no? The syntax that is very commonly used with Python users, no? And in other libraries. No? And you can have operators like computing the minimum value of an array or performing the transpose. No? And we have also operations to iterate on the DS arrays, and then, for example, you can apply external functions based on these iterators. No? So you can build up from the operators that the dislib have, okay, and not this to run. Okay, already said this. Okay. This is a bit the collections of methods. I think it's complete. And I reviewed the documentation. So in addition to some methods for recreation, loading from different files, different type of files, some of them you will see that are specific for some life science data files, because we had some others from life science that were requesting them. So if necessary, we can always expand it for needs of the communities. Okay, we are open to this. We have some utilities for accessing this data and operating only on the data. And then different methods like the PCA that can be applied to reduce the number of features that you will use later in another analysis. Then we have some matrix decomposition functions, because they are used as auxiliary in other methods, or because we have had projects where we were going to use like this UR. For clustering, well, you have seen it in the demo before the K-means, but without the dislib. But here is integrated in the dislib. What it means that it's integrated in the dislib, that uses as data set the DS array. So the code is a bit different to the one that Javi was showing, although the idea is basically the same. We have other clustering algorithms. The DAURE is one very specific that is used in the molecular dynamic area. Okay, but this is the name of the author. For classification, we have a variant of the support vector machines that we will see the example of the code, how it works, but it decomposes the DS array or the data set in blocks and then operates in the form of an inverted tree, no? First with the more parallelism and then doing a kind of a reduction. We have the random forest and decision tree classifiers. We have ALS, which is a recommendation algorithm, the original from Netflix. We have some algorithms for regression, based some more general, others more based on trees, network queries, and then also this set of methods that can be used, we'll see in the hands-on or in how to use them, or in the demo also, to find the best parameters for your methods, no? Find the methods that enable to get more accuracy and better training with the different methods. And this can be also extended. Any of the areas can be extended under demand or because you request or there is a need. This is a bit some results, because in the morning there were some questions about performance. Okay, so I added in this case for the dislib some charts just to show a bit how it behaves. No? In this case, we are running with different nodes in Mare Nostrum, so up to 1,500 cores. Okay, and in this case, is comparing the dislib machine learning with another library task.ML, which is based on a similar programming model that is called Dask, and also against MLlib, which is the machine library of Spark. This study was done a few years ago, but I'm still using the charts because more than for me more interesting that the fact that this leap is faster. Here is time, so less is better. You can see that for those that I have the values for the comparison, this leap is running faster. But here, what is even more important for me, that why I don't have here the results from the other two, because they could not run, because the memory was, here we are using 2 billion samples, each of them 600 features. So with these two others, they were not able to run due to memory problems. Okay, so, and this is one of the strong points, no, of this leap, because they are run below with PyCOMPs, is that they enable much larger problems than other tools that are based on having all the data in memory. Okay, so that's why I like to use these charts. Okay?
Can I ask a question for that graph? Why not the time decrease linearly?
No, because here you have 48, 96. So
oh, it's a long.
yes, it's no, it's not long, but here you have 500. So when you double, we expect to decrease by 2. So here is 500 something. The expectation would be with the double number of cores to have like 250 something, 260. Here, so what you're saying, it will be the speed up curve that we don't have it here. In fact, at the end, it's not the scaling very well. Here, we have worse results here. So I think we probably the granularity then was too fine for the runtime. But we were not expecting linear here. We were expecting every time dividing by 2, because we are multiplying by 2. If it was a speed up, you will expect every time doubling the speed up. But this is time, so you expect every time you double the number of cores to reduce by 2. Okay? And yeah, here the points are 48, 96. You understand?
Yeah, I understand.
Okay, I can explain it, but it is better maybe in the like.
I still quite understand. I mean, I understand your meaning at like multiply by 2 and the time increase in half. Yeah, I've been checking.
This is approximately the half.
Yes.
In fact, the other problem is that this is not the 0. I think this is also making worse
So you said that you were using this library, dislib, without touching anything, just downloading it and as it is, or just tuning it?
Is our library.
Yes. So I'm talking about when you tune that or you configure it, compiling with extra parameters or just as it is, conventional features as it is. Yeah. I mean, in order to manage such large sizes.
No. What is tricky with the dislib, I'm going to speak about it later, is defining the block size, because although the parallelism is transparent to the user, it needs to define the block size that it will use. If you use a very small block size, you have more parallelism, but you will have more overheads. Okay, and the task can be very small, and then maybe there is overheads there. If you do very large block, you may have memory problems because the block needs to fit in memory. So this would be the point that is tricky depending on the algorithm. We are now collaborating with another group in order to be able to define this more automatically, like a kind of recommendation tool to say, okay, the best block size would be this one. Okay?
So as always, it's application dependent. Yeah.
This can be on one side application dependent, depending on the task graph that is generating, and on the other side on the actual system that you are using.
Okay.
Because if the system has more or less parallelism or more or less memory, the optimal block size can be different.
Yeah, sure.
Okay, so just to revise a bit the basic concepts, probably most of them you know, but just to do a bit starting from the basic, no? The basic of the machine learning algorithms that you can have unsupervised methods and supervised. No? So for unsupervised, what the algorithm does is find patterns, no patterns from labeled data that is not labeled. Okay, and this is, for example, the clustering. We'll see example in the next slide. or supervised that will learn from data that has been already labeled. Okay, and this can be an example of classification. No? For example, no, you saw the k-means before. No, we have unlabeled data. We have some points, and we don't know any specific if there are any category or anything between them. And in this case, we are looking for clusters, no, and also for the center. No, once we have got this information, is maybe then we can label the data and use it for a classification problem. No? This could be what the clustering does. No, but the classification, for example, what you have is the points that already have a label. No, you have the red points and the blue points. And what the method tries to find is some relationship between them in such a way that when I have a new point, I can predict if the point should be labeled red or blue. Okay, so this would be the basic difference. And so then how we use this in libraries like the scikit-learn, this is like the model that we are using for dislib. So it's based on an estimator that would be anything that can learn from data, no, either label or unlabeled, and basically we'll have two methods, not the fit, or that will be the one that is training, no, it will use some input data to build the model, and then the predict, that once you have built the model, you have a model, you use it for prediction, no, for inference. And the typical, this is in dislib, okay, although if any of you know about scikit-learn, you can tell me the differences. In this case, we have a couple of methods for loading the data. Okay, once we load the data from a CSV file, the trained data, and the difference here is that we are using the block size. So this is load test file is a method from the dislib that will load the data in this array X that will be a DS array. But in order to become a DS array, you need to indicate the block size. And we'll split the data in blocks of this size. And here we have then loading the test data, for example. So we will use also the same method, but you store in another array. Okay, and then in this case, the same block size. Okay. You instantiate the method. So until here, nothing different. It's passing in the same way the number of clusters that you look for to use. No? You call the feed. Yeah, passing the X, and then you can predict on the test data. Okay. And as you see here, it says nothing about parallelism, nothing about PyCOMPs, whatever. So what it does internally, no? So internally, what happens is that we have the different data and methods parallelized with PyCOMPs. Okay. So then the DS array has as basic unit the block size, and the blocks can be NumPy arrays, which will be continuous data, no? And then also we can work with the sparse data, okay, with the SP matrix, okay. And this also again is transparent to the user. You just instantiate the array as dense or as sparse. And then you have the methods that internally are parallelized. No? Here, for example, this would be two different calls for generating data or modifying data. No? This one, DS random array, is creating a DS array with random data, in this case of 100 by 100, in blocks of 25 by 25. Okay? And with this call, you will have this X array that is of 100 by 100. The organization, in fact, is something internal, so you doesn't care. But what happens when you invoke this method? In fact, it has an iterator, which finally will invoke this task here, this PyCOMPS task, which is calling this task random block, which giving a shape and a zip will generate a random block of the shape that we were saying, and the shape is the block size. Okay, so this will be calling, in this case, 4 by 4, 16 times this task to generate the 16 blocks and organize them in a single DS array as a list of lists. This other one, for example, is applying the function min to compute the mean along one axis of the DS array. The array is a matrix. So if you apply to one of its axes, it's computing the mean of the different rows or columns, depending if you use one axis or the other. In this case, this apply alone axis. This is part of this code that will iterate on the axis that you are passing. And then all this block apply axis, which is a task again, which you pass then the function. In this case, the function will be this MP-min. Will operate on the block, okay, passing this function, okay, and will compute the mean, or for example, a column of the DS array or column of blocks. Yeah? This will be, for example, part of this block. Can be a list of columns. Okay, I was for another fix x0 will be the set of rows.
Could be columns. Could be columns.
I always for x. Okay. So and then I mean we can use these tasks that are auxiliary to build other more complex functions. And this is the basis that we use, for example, for operating on data. Okay. Another we haven't seen the collections, right, in the morning.
Yes.
Yeah.
So the collection, you can see here that it uses collections also. Okay, in this case, the blocks is a list of with that. Okay.
What's question? What would be depth 0? What would it represent?
Depth 0, it doesn't exist.
So depth 1 is just
The first level.
Yes. It's just one list with the elements.
The first level of elements, and if you do 2, we'll go inside one level more, and so on. If you say nothing, it will look for all the levels.
Yes.
If you say the level is better, because then it's kind of an optimization, because it will not look for the dependencies in all the possible levels that this data structure may have. Imagine that in fact the collection have more levels. Then if you don't say anything, PyCOMPs will look in all the until the last level. So you can say, okay, I don't need this, just look until level 2. Okay.
What does that level exactly mean? That level.
The list, how many elements are inside. So you have a list, and if only first element is 1 level. If it's a list that contains list, that's a second level.
Yeah.
So, but if it's
This
matrix,
would be level 1, for example, a single list with only 1 level. But if this is, for example, a list of lists, and we want to go in there into this list of lists,
Then
we can say that it's 2.
I mean, it's like, I think we're talking about matrix here. So if a 3-dimensional matrix, the level is the same.
Yeah. Exactly.
I got the level.
But it's not necessary for you to define.
Yeah, I mean, but I don't know whether I should define all of this.
Okay.
I don't get it.
Yeah, la media es okay, then just to see a bit more how it looks. In this case, is the support vector machine, which is a special implementation of the cascade-based super vector machine, which we based in an algorithm that we had a reference. Okay, that we were comparing. That divides the data sets in blocks, okay, and then you perform the CSVM on that block, and then you use the result with a kind of a merge function, okay. You append the data, and again you call the CSV with the result, and so on. No? So this will build in terms of function, it will be like a kind of an inverted tree. Which first, the first level you operates on each of the blocks of the DS array. Okay, And then it will use the result of this one and this one to do another training here, the result of this one to another training, and so on. So this is the basic structure of the algorithm. Okay? And you can see, that in the main code is the one it's above. Okay? We have a global while, because in this case it will do multiple iterations until there is a convergence criteria. It's not, okay? So it checks the conversions, and if not, it calls the iteration, the do iteration. Okay, and this is like the body, part of the body of the do iteration. And we receive the data X and Y, which is partitioned in blocks. Okay, and then for each of the pairs of partitions, we call this training, which is we will see that is a task. We will see in the next slide. Okay. So here we have a first level of task that will represent this first level here, okay, and then the results are appended into this list queue, which later will be also be traversed, okay, pairing the data again in pairs of two or more. Here with the arity, we mean that you can take two, as I showed in the example, or maybe more nodes because you are interested in doing a faster tree, okay, with less levels. And then again, it calls the same function. And this train function, as I said, is a task, okay, that operates in this input data. And it's then using the scikit-learn as a basic operation. The call to the support vector machine function method in the scikit-learn as a basic operation. And on some of the algorithms, we do this. Okay, we have an algorithm which is iterative or whatever, calling multiple times a function, and that it ends up calling a function from the scikit-learn. Okay, so internally we use scikit-learn in some of our methods. Okay. Again, it uses here the collections. Okay, and the two. And this will be the user code, no? So you see that still is simple. Instead of import, if this was a scikit-learn method, you will be importing instead of this lib the scikit-learn, and here whatever was the method for the scikit-learn. In this case, we are importing the dislib, okay? And then you load the data, for example, you instantiate the method, and you call it. Okay? And this is the user. This generates a task graph. In this case are two iterations. So this iteration will be one iteration here of the, so here we have a loop, no? While self, this while not self, we'll have multiple iterations, these two iterations. So this, each subgraph here is one execution of the two iteration. And as you see, you have, but in this case, it's not exactly the same here and here, because the first level we have the task that load data in blue, and then we have the white, those are the other data. No, this is another one. Sorry, this is already operating on the first level of data, and then we have the reduction of the different levels of the algorithm. Okay. If we generate the trace file, okay, you will see this tomorrow.
Yes, excuse me. In the previous algorithm with the CSVM, what you do is at every level, you basically relabel each data point. That's right. Relabel the data point.
The data point.
Where you give them a label, blue or red. That's my question.
You mean this?
Yes.
In the classification part, but the CSVM, not the graph. The graph, this graph has graph.
The CSVM. That's what you do. You give.
You classify them.
And then throughout your iteration, you refine the label. You change them.
Exactly. It's a refinement because each of the nodes is learning only in a part of the data. And then you are kind of readjusting the model. You have this partial model and this partial model, and you the merge, in this merge here, you will readjust.
And then the question that comes to mind, at least to me, is does your arity, the
which is
Does it? Sorry.
the arity.
Arity. Impact.
Will it influence the end results? In some cases, I would imagine that it could, not just the speed. Is it something that
My intuition would be that yes, that the arity can affect, because if you are using more information in the same level, you can end up with a different model than if you don't. Yeah, exactly. I don't think that it is exactly equivalent if you have different arities. I don't know if we look into this when we did this algorithm, but it's true.
might
Probably.
be interesting to
Yeah,
It is-
probably interesting to check,
run it 2 or 3 times, randomize and see.
see how it changes. Yeah, it will be interesting. This is an algorithm that it was generated, it was defined by Julie, group working in Julie and in the University of Iceland. But they were using for parallelization MPI, which is a programming model. And then we did an equivalent version, but with the dislib with PyCOMPs. And well, the idea was to compare with the performance, no? Well, at the end, we didn't do the paper together, but well, we published some of these results, okay? But I don't think this was a former colleague. I don't know if he was comparing how the arity, but it can be interesting, yes.
It's just one hyperparameter, so.
So it's true. Okay, so tomorrow you will see.
I'm gonna ask a question for the previous slide. I think maybe I'm just beginner of the distributed. I don't really fully get the idea. Because I'm actually from AI for super vector machines, we are actually using the full set of the data because we are looking for a hyperplanes in the data, like the very fast in the place to separate the two or multiple categories data set separately well. So you are dividing the data into a small like block size. And created a new classifier, yeah. For
Well,
each
it's another way of doing the classification, where you decompose the problem into subproblems.
Yes.
And then you try to train each of the subproblems separately, and then combine the different models in an iterative way. Okay.
Explain one more time how to combine them in the iterative way.
I think if you don't mind, I'll explain it to you later on, because I think we will run out of time. Let's speak later in the hands-on, okay? So tomorrow you will see a bit more about these trace files, but basically this is a visualization of the execution of the application. And again, we have different colors for the different tasks, okay? So the blue ones are reading the data. This was a former version of the algorithm that had 2 other tasks. I realized when I saw the diagram, sorry. But basically the ones that we were saying, the training will be this pink one, okay? And these ones are used at the beginning, Gen IDs and so here when we have different lines, it means that a processor is running this task. Okay, when there is nothing here, it means that in fact the processor is idling. So in this case, this algorithm, due to the configuration it has, we don't have, at the given level, we don't have more parallelism. So there is 1 or 2 tasks that are at most running, and the others are not running. So this may happen because of the algorithm. In this case, we don't have more parallelism. But what we try is to exploit at maximum the possible parallelism when there is enough tasks. Okay? And here what you can see is the different iterations. Now this would be 1 iteration, of the 2 iteration, this is another one, and so on. Okay. So this is a way of seeing the performance that you're obtaining with your algorithm. Because you can see which tasks are run at a time. If one task takes more time, maybe you think that all tasks take the same time, and it's true. Some tasks can dominate the time, etc. Okay. Another thing I wanted to show you is the website of the dislib. So from the website, you can browse the documentation. Okay. We're trying to maintain all the methods documented, but sometimes I don't know, this is documentation. We have a quick start, which if you plan to use it, also it's good to have a look. Okay. For today, for the hands-on, we will use the same environment that you've been using before. It's already has the dislib installed. Okay. But here it has also how to install it. Okay. In case you want to install it in another system. Okay? And you can access also the API reference. Okay, we have documented all the different methods and with the different parameters and whatever. No? So the SVM. So you can go over there and you can see the parameters that you have. You have an example. Sometimes you have more than one example, etc. Okay, so it's quite well documented. Okay, and then also the code is open source. If anyone wants to say, "Oh, I would like to build a new method," you can try to do it yourself and ask for being a contributor. Okay, but also if you want to install from code. From the source code. Okay. And we have also some notebooks and some examples available.
I'm Christian, and I will be presenting the hands-on and the demo for the dislib. So without further ado, we'll be going to the terminal, and we'll be starting again the environment, the same environment as before, using the PyCOMPSs with the Docker and with the Docker environment, using the same commands as before to start a new Docker environment with PyCOMPSs.
The tutorial apps folder inside Python. I hope everyone is hearing me okay now. Notebooks. Here in syntax, we'll have some. We'll have our notebooks that are interest for us. So for me, I will just execute the PyCOMPS init command. Inside here with the 3.8 image. Okay. The environment is created, so now I will just run Jupyter, and it will execute inside this route. And I will open it with my web browser. Okay, so the one that we are interested in, it's this one, the 9 dislib demo first. Okay, so yeah, basically right now we'll be doing the same thing, running the PyCOMPS runtime, executing it. It will start up. We'll import dislib exactly like you will import sklearn. It will be the same thing, importing dislib. And right now, the first example will be to create the first distributed array. The DS array will be a NumPy array with a shape of 500 by 500, but it will be split into blocks of size 100 by 100. So at the end, we'll have a data structure, which is the distributed array that will contain chunks of 5 by 5 blocks. There will be five blocks in the vertical axis and another 5 blocks in the horizontal axis. So in total, we'll have 25 blocks. So running this you can see here there are some attributes that the DSRI have, like the shape, the original shape, the whole shape, and also the regular shape of the blocks. This is the shape of the blocks inside the DSRI. So we can access the blocks with this attribute, which is like a private attribute, but we can access the blocks inside the DSRI using this line. But right now, all the blocks are future objects. That's because they are not right now loaded into memory into the master node. So they are future objects that they will execute on the workers node. In order to access the real information inside the blocks, we'll need to run the command collect. So every DSRI has this function, this method that is collect, and what it does is it's basically gluing together all the blocks back into the original shape. So right now we have the original DSRI of shape 500 by 500, and now we can access the blocks inside each list of the blocks. We can access the blocks, and we can, like any other NumPy array. Moving on, that was a way to create a random distributed array with random numbers, but you can also create a distributed array with hard-coded number with any type of values. And this time I will have here 2 rows of a matrix with 3 columns, and I will split them in blocks of 1 row by 3 columns. So that will mean we'll have 2 blocks in the vertical axis and only 1 block in the horizontal axis. Yeah, and so the shape of this array is it's 2 because there are 2 rows in total, but every block will have 1 row only. We also can create these arrays with blocks that are sparse, not only with NumPy. So it's also a feature that a distributed array has, just because so many times you will have data that has so many zeros that you will want to compress them in order to have less overhead at the communications, and you will want to use a sparse matrix. So you can also do that, and you will see here that the sparse parameter is marked as true, and before it was false because it was just a NumPy array of full of a dense matrix. And we can also do the same thing, collect all the blocks of the distributed array into 1 single block, and it will return just the sparse matrix. This is an example of how would you load a file into a distributed array. The dislib has already these utility functions that will read a file and just load it automatically into chunks, into blocks, and combining them into this data structure. This format of file is SVM. It's known for saving sparse data. So this one it's also a sparse distributed array, and you can also load CSV files like normal TXT files, and they will load just fine without the sparse parameter. Like we try to have the most similar API to NumPy using this distributed array, so you can also do slicing of the DSRIs. Here I will create this array of total shape of 50 by 50 with block size of 10 by 10. So I will have 5 by 5 blocks, which means 35 blocks in total, and I can access a specific row, which be the fifth row in this example, and this 5th row will have, the expectation will be to have only one element in the first dimension, which is the only one row, and 50 elements in the other direction. The thing is that this slicing, it does not return a NumPy array, it returns another distributed array, because inside this slice, I will have just one row of blocks, and this one row will have 5 blocks inside. So this is another array. So I will have to collect this one just to obtain all the numbers, all the 50 numbers in the row. Yes. Mm-hmm. The features will be the dimension of the vector. So exactly, each data point will have 780 dimensions. Yeah. Yeah, it's a table. Yeah, it's we can see here we'll have the shape of this one. It's 61 data points, and each data point has 780 dimensions, features. So it's just like a regular. It's like a regular CSV file as well. This one will also have. Let's see. 5,000 points with 122 columns. So this will be another table. Yeah. Yeah, inside this file, inside the SVM file, there will be like 2 datasets. So you load one dataset, which is the X, and another one, which is the Y. And the Y, let's see, the Y should have only one. Also, you can access just a single element, not just a row or a column. You can access just a single element, and that will be one of the points inside the array. And yeah, not only consecutive or consecutive rows or columns, but you can also access non-consecutive rows or non-consecutive columns, just like in NumPy. And they will give return another DS array, and yes. Here it's a slice in both dimensions at the same time. You will get just like a block, like a 5 by 5 DS array with only a shape 5 by 5, and that's it. And also you can execute exactly like in NumPy functions that operate over these arrays. In this case, it will be to calculate the mean of all the columns in the DS array and collect them. In this case, there's the sparse matrix, because I think I didn't run this one before. So right now this will be the mean of every column. That's the axis Y 0. So axis 1 will be all the rows. And also, you can also transpose exactly like in NumPy, but here the difference with transpose will be that in NumPy, transposing a NumPy array will not move any data around. It will just mark the NumPy array that it will need to iterate over the rows instead of the columns, or vice versa. But here we'll have to physically move the data, because all the blocks they will have to be transposed the data will have to be transposed in the blocks, and also they will be you have to reorder the blocks inside the DSRI. So this one does make some work comparing to the NumPy implementation. So this one will be an example of how you can use dislib, which is a machine learning library, to do machine learning. We'll be demoing k-means in this first example. Right now, I will just load a synthetic data set from scikit-learn. It will just create blobs that you will have to clusterize. Here we can see that there are just 3 clusters easily, and right now we'll just have to convert these X and Y arrays into this array, into distributed array. So right now my data set has 1,500 points with 2 dimensions, with only two dimensions. So I will just create the distributed array of that NumPy array and split it into blocks of 3,000 by 2 columns, 3,000 rows by 2 columns. So that will give me 5 blocks by 1, just 5 blocks in vertical axis. Yes, and now we can just run the clusterization over this distributed array. We will just import k-means. We will just say, like an example, 2 clusters, because supposedly we don't know how many clusters there are. So we'll try to guess. And yeah, just run in fit, exactly like in sklearn. We'll wait some time, and yeah, the fit it's already done. We can see the centers. It's already computed some centers for us, so we can now like clusterize officially the dataset. We'll have in return another DSA array that will represent in which cluster every point has landed. So with this example, we will paint which cluster it's where. Right now, yeah, apparently it's yeah, with two clusters it's not very good. We will try to increase it to 3 in hope that it will get better, but we can also see the centers of every cluster, and yeah, just change it here the parameter, run the fit again. The centers, yeah, there are now three centers. The predict again super fast quickly, and now yeah, everything is okay. This right now, this is like the final of the end of the first demo. We can just go ahead and stop the Jupyter runtime, and we can access the monitor also. I could, if you don't have the monitor started, we can just in another terminal, we can just start it up right now. PyCOMPSs monitor start. Open this link to our web browser. Currently is loading. Let's see. Okay, so the username for the monitor will be root again, because everything that is running inside the Docker container is running as root user. So every time you have to get inside here, like root. So here we have our application. The whole notebook has been parsed into a task graph. So let me see. A bit of zoom. Yeah, at the beginning, we have all these tasks that are for creating the data sets, or creating the different these arrays of the beginning, for the slicing, for everything. And afterwards, we'll have the execution for this, for example, this large one, I think will be the k-means. because it has all these reductions or these iterations inside. And this one is the k-means, and all the width of every tree inside this dependency graph, which is these green tasks, depend on the number of blocks that I set. In this case, I think I have 5 blocks for the data set, and in this case, it ran 5 tasks in parallel. So that this is the trick for the distributed array. If you want more parallelism because you have more cores or whatever, you can increase the number of blocks by decreasing the block size, but that will generate more tasks. So maybe that's something that you want, or maybe that's something that you don't want. Maybe sometimes if you have too many tasks, it will get worse instead of better. Yes, and at the end, just the final synchronizations. So this will be the first demo about the dislib with some basic primitives and basic functionality. We'll go to the second one, but before this, some questions here. Everyone got it work perfect? Yes. The legend, you mean? Here. Here. So you mean in how translates the task graph to the code? Okay. Okay, this form, I think that at the beginning, the first thing we did was to create a distributed array. So for me, that will be this task right here, because they were not depending on anything. So we'll just create a distributed array, and for every task, they will create a block. Yeah.
So probably when we access the object.
See, every collect will have to stop the execution in order to get the blocks. So that is the synchronization point. That's it. Yeah, it's not obvious. Yeah. Also, the k-means algorithm has an iterative while loop. So every time it has a synchronization. For every loop, it has a synchronization just to check if it converged. Okay, so this one, the first one, just for like introducing, we have another notebook, which is the 10.0, which is like an exercise for you to, and for me to complete all the blanks that have that are in the code in order to execute and learn a little bit better the documentation and every functionality of dislib. We'll just open it and execute again, running the PyCOMPSs runtime, importing dislib. Right now we'll have an example using again clusterization, but this time using dbScan instead of k-means, just to compare the two of them in different datasets. Creating the dataset, again, some blobs from sklearn, the same one apparently from before. Create the DSRI, convert them again to blocks of 300 by 2. the dislib algorithms could run, because if you try to call a dislib method with just a numpy array, it will fail, because every dislib method needs a distributed array. So right now we'll just try to use dbscan to clusterize this data, and in order to do that, we'll try to complete these parameters for this. Let's look a little bit at the documentation, at the API reference for the dbscan. Maybe I should show you how to just get inside here at the dislib documentation. Just go at the API reference, and then here you have a full list of all the public functions of dislib, and dbscan will be here at the clustering category. And yes, you'll see here a description of all the parameters, what they do, what are the default values, a little example, and also the public methods that you can run. Very similar to Scalar. So for this one, we'll have to give 2 parameters, epsilon and the minimum sample. So epsilon will be the maximum distance between 2 samples in order for them to be considered in the same cluster, and mean samples, the same thing, but with the number of points. So let's try here 0.1 and 5 minimum samples, just to have that will be the Euclidean distance between the points. So if you are if you need to normalize, you will have to do it before. Yeah, in the real world, maybe the data will not be that clean like the one that Scalar gives to you. So you'll have to make a pre-processing like a min-max scalar or standard scalar. And for that, we also have functions. We have here in the documentation, we have at the data processing, we also have the min-max scalar and the standard scalar. So if you have some crazy data, you can also use it with these kind of functions. So we'll just create the object, and here using the predict function, just to clusterize everything, dbscan fit and predict, which is here, fit and predict with only the X with only the X dataset. So we'll execute that. Now it's running, and we can plot it with matplotlib. Here I had to collect it, because in order to plot it, you have to have a numpy array, and if you try to give it to this array, it will just explode. So you have to collect it before and just give it to you. Yeah, so this clusterization, it's not okay. Let's try to change the distance. Let's see. Yeah, here it's better. Yeah, you have 3 clusters and another one which are supposedly the outliers. Maybe if we increase this one to 8. Yeah, something like that. This is an example to show how the difference between k-means and dbscan in dislib. We have 2 different. We'll have another dataset which is not 3 blobs. We will have 2 circles, like 2 rings, one inside each other, and we'll try to compare how k-means and dbscan will clusterize this dataset this time. So right now we'll have to do the same thing, but with the k-means. We will have to complete here, create a DSRI of the new dataset. So there will be the DSRI, the X in format NumPy, and with the block size the same as before, 300 by 2. Importing k-means in the same package as cluster from from cluster as dbscan, creating the objects for k-means. In this case, n clusters. I don't know. I think 2 or 3 clusters will be okay. Let's see. And dbscan was the everything in. Yeah, and the epsilon again, like 1.5 means sample is 10, for example, and just the fit and predict exactly like before. For the k-means will be fit, predict with x, which is the DSRI converted, and with dbscan will be exactly the same. And yes, thank you very much. Let's see. Yeah, apparently it's working okay. We are clusterizing. So right now, every fit predict will return another DSRI. So that's why we'll have to collect them in order to plot them. Okay, so in this case, dbscan clusterize everything at one cluster, and k-means just split the whole plane into 3 regions. Maybe we can just make it better this way. Yeah, with k-means, I don't think we will get better, but with dbscan, I think we can. Yeah, this in this example with these parameters, dbscan got a better result, and k-means is just not working very well with this data set. That was the part of for clustering with dislib. We also have a second part, which will be the classification using also some algorithms from dislib, like random forest and CSVM, the cascade support vector machine. So for that, we will just load this example dataset, which are digits, images of numbers of pixels, 8 by 8 pixels. That's why they are like just in a row of 64 pixels, and we'll just the number the 24 element will be values from 0 to 255, I think. So we can just plot it, and this one supposedly I think it's a 3. Yeah, here it says it's a 3. The Y dataset will contain the class for each digit. So the Y array will have values between 0 and 9, and we don't want that. The example we will try to do will be to just have a binary classification. Although you can do multi-class classification, we can, in this example, we'll just convert all the classes into even or odd by using the modulo operator. So right now, this number that was 3, right now it says that its class is 1. That means that it's odd, and yeah, right now if we run the unique, we'll just have 0 and 1 for all the numbers. Next step will be just to have like a little a separation between the data set for the train and test, just to compare how good are the algorithms for classification. We'll just split it by 2575, train and test, and create convert those splitted arrays into distributed arrays. So for the train one, it's already written, so we'll have to do the same thing for the test one. So it will be again this array with the x test and block size of 300 by 64. One important thing for some algorithms is that you will preserve the block size of the different distributed arrays that you are using. Sometimes there are algorithms that they do not support operations with different block size for multiple these arrays. So that's why it's pretty safe to maintain the same block size for the distributed arrays that you are using. So this one will be the ARY test, and with just one column. Okay. And right now, creating the cascade support vector machine, we can to see how to create the object. We can just look again at the documentation. Let's see, this will be in the under classification. We'll have cascade vector machine and k-neighbors. Let's see inside cascade vector machine, and here we'll be interested in two parameters: C, which will be the penalty for the error, and gamma. So let's see, for the C, I think we should try VM value of 0.1, let's see. And for gamma, I think 10 will be a pretty good start. Right now we'll have to fit this estimator, which it's exactly like before. Let's see, cascade. Okay, support the machine fit. Let's see, fit will need here, we fit X and Y, which are the train distributed dataset, DSRI, and the Y distributed train DSRI. And then we can just run these commands, and afterwards we'll see how to get the score. So for the score, we'll try to use this this function that the model has, which is here at the bottom, score, that returns the mean accuracy. So we'll try to do that. CSVM with score of the X DS test and Y DS test. The thing is that the score that you will return will be a future object, because all this let's see, print. All these executions will run asynchronously. So right now, when you are executing the line, you will get just a feature of it that it will get resolved on the future. So for that, we will just need to use COMPS wait on, which tells the runtime to wait for all the tasks that are required to run in order to obtain the result. It will wait and it will return the score. So right now it will just execute. Yeah, you can see here it's pretty computation intensive. The support vector machines, and it's already finished. The score will be 0.5. Okay, maybe the random forest classifier will do it better. So we'll try to do the same thing, but with random forest. Let's see. So random forest classifier, let's look it up on the documentation. It's at the bottom of the page on trees. So random forest classifier, it's under trees. In order to use it, we'll have a little example here. We need to import it from dislib trees, random forest classifier, like that. Okay, and create the object. In this case, you can just specify the number of estimators. For default, it's 10. I think that it's a pretty good start. I will just leave it like that. We'll have to fit it again with the same dataset as before. X distributed array train, and Y distributed array train. And yeah, we'll just feed it. It already returns, it already executes. So now we can just get the score. For the score here at the documentation, you can see that it has a parameter which is collect equals false. So this one, if you will try to use it, random forest score, again with the same thing as before with the test data set. If we pass collect equals true, it will do the same thing as the COMPS weight on, but just behind the curtain, so you don't have to do it. So right now, this score that it will return will not be a future object. It will just wait automatically for it to complete. So yeah, now the score it's much greater. So the thing is that the cascade support vector machine it was bad. The result was very bad. So we want to improve it. We don't know which parameters are the best in order to do that. So we'll have to run a little hyperparameter optimization. So for that, we will use another utility from the dislib, which is the grid search. The grid search right now will run it for the cascade vector machines. So we'll have to instantiate the object. Search CV, and let's see at the constructor what it needs. Model selection, grid search CV. So it needs like estimator and the parameter grid, two mandatory parameters. So the estimator in our case will be the cascade support vector machine that we'll want to optimize, and we'll try 9 combinations of these parameters, gamma and C, in order to obtain the best combination. So the grid search is doing basically that. Params, okay. And yeah, afterwards we'll just have to fit, I guess, yes, fit, and that will search fit with the X, with the X and Y. Yes, train X, yes, Y. Yes, that's right. Okay. Okay, so right now it's what is doing behind the scenes. It's let's see the activity. Yeah, it already started. It will run 9 different cascade support vector machines models in parallel, and with this 9 unique combination of parameters, which is the Cartesian product of the parameters. So at the end, when it will finish, it will just return us the best combination. Well, it will return us all the result for all the executions. So we will have to pick somehow the best combinations. For that, we'll use pandas just to parse the table and to make it look a little bit better, and we will print the combination of the parameters that run for each simulation and the result, the score for that parameter. So we will see at the end a table with which were the best and the worst combination of the parameters. Yeah. So yeah, here will be. In the meantime, I will. If there's another. Yeah. Okay. See. Ah. Yeah. Okay. I will repeat it. The question was that before here and at some point, let's see, for example, at here. If you forget to do a collect or something like that, the runtime will crash. So you will receive an error saying that it was COMPS had an error, and you have two options. You can continue the execution of the Jupyter notebook without COMPS. So that will be one option. And the other one will be to restart the runtime if you want to continue using it. So if you choose to restart the runtime, it will restart. It will start from the beginning, the runtime. So you will have it will forget all the data that has been generated so far. So in order to continue, you will have to create again the data and get again to this point in order to process it. That was the thing. And also, if just clicking the box for restarting the runtime is not enough, you can also have this option for restarting the kernel, and it will clean up everything, and you'll have to start from the beginning, starting the runtime again and importing dislib and everything, importing all the things again. So apparently it already finished, and we have all the combinations for the parameters. Apparently the best one, I think it's the last one, yeah, with 98% accuracy. So we'll try just to use that here. For the gamma, it's and for the C it will be 100. So this one will have to be the best combination. Let's see, executing again with the trained data set and the test. So yeah, right now the score is much better, and yeah, everything's thanks to the grid search of dislib. Now we can go ahead and just stop the runtime, and that will create again the task graph. So we can see it on the monitor. It's still it is right now when all the stars on the last line have appeared. Right now it's completely stopped. So let's see. Yeah, it will be in the same application because I had the same execution from before, or maybe not. Done. Ahora más alto. Oh, see. Okay, so there's another application. Yeah, I thought it was the same one. It's another application. We'll have to select it. Muy bien visto. And right now it's loading the complete the task graph for all the tasks that have been executed for the support vector machine, the grid search, the random forest, everything. And also, in the meantime, there's no another question. No. Okay. So in the meantime, we also wanted to show that we only showed just some functionality of dislib. There's so much more. We didn't even talk about matrix decomposition or the neighbor queries, the neighbor KNN classification as well. For the last release 0.8, that it's right now 0.8, the last release, we also included support for GPUs. Here in the user guide there's a category, it's a section for using GPUs for with dislib. That will mean that these algorithms in this list, K-means, KNN, PCA, QR, SVD, and all the others like basic operations of arrays can use GPUs from NVIDIA only. They using CuPy behind the scenes, so they will only work with NVIDIA GPUs. And the only thing that you need to make it work is to install CuPy. The required version will be at least this one, 0.9.6. And just before running the application with run COMPSs, for example, have this environment variable set to true. So dislib would automatically detect that, and it will use the GPU every time it can. So that will be automatically that's the only thing that from the user point of view has to do. Mm-hmm. You will need to create the code in Python with the distributed arrays, and in the moment that it will work with normal CPUs, you can just export this variable and set it to true. Have CuPy installed, which is the NumPy library that uses CUDA for NVIDIA. Yeah. CuPy, it will move the blocks from the main memory to the GPU memory. Exactly like that. But in CuPy, it's CuPy.asArray. So it's just another name. But I can show you an example right now. Let's see if, yeah, we have the complete task graph. Because sklearn under the hood, it also uses NumPy. Yes, so every NumPy array can be converted to CuPy array as well. So our implementation for the dislib, it uses sklearn for CPUs. And when you're using GPUs, it will use the CuPy arrays and use the primitive functions from CuPy, like matrix multiplication, summation, addition, and everything. Yes. Yes. In this case, dislib will do it automatically for each task. At the beginning, we'll move it to the GPU, it will do the computation, and will return to the main memory. I think it's too big. Yes. This one. For the complete, I think it's too big to load for my computer. Let me refresh. Yeah, in the meantime, while it's also loading, I can show you a little example from the GPU implementation. Let's see, neighbors, base. So this is KNN. This is K neighbors classifier, and here you have a task that uses GPUs. Yeah. Sorry. This is the task that uses GPUs. It receives NumPy blocks. It glues together the blocks into one NumPy array, and here using CuPy, it's moving the data to the GPU. Here it moves the GPU, then the GPU computes the distance between the nodes using the Euclidean distance. Also some other operations inside the GPU, and just at the end of the execution, it will just return the normal result from the GPU to the CPU, so it can be transmitted to another nodes afterwards. So this is the normal functionality. Yes. Exactly. That's why you need to control the block size. Depending on the block size, what? Yeah, this is the merging of the rows, not the whole data set, because you need the rows. Yeah, because you need to compute the distance with the whole vector inside the GPU. So that's why you need to fit. If you really have some memory issues, in the case that the one row can fit in memory, yeah, that would be very extreme. But I think that will be also limited by the hardware, because the GPUs have so much less memory than the main cluster. For example, you can have a node 100 gigabytes of memory, but the GPU will have so much less, like 10 times less. So yeah, you will have to control the block size, are very important here. Yes. Mm-hmm. Yes. Yes, because well, sometimes can be more than it depends on the number of GPUs they're using, but the speed up, I think the speed up will be at least I think will be, I don't know how to say it, because every time we have to compute it with the different numbers of GPUs, I think the speed up will be compared with 4 CPUs and 4 GPUs, for example. The speed up it's more than 4. It's so much greater. It's
I think so.
yes, yeah. That depends also in the size of the blocks. If you have large blocks, you will get communications overhead and the other way around. So it's a trade-off at the end of the day. Yeah, this one I don't think it's moving. Yeah, I'm trying to unzoom, but
Sometimes.
Sí.
Oh,
mira.
Ahora aparece.
Dios.
Was lost in the middle of.
Sí. Wow. Yeah. So yeah, at the beginning you can see the k-means that we run, the random forest, and all this train of tasks will be the grid search. The grid search that inside will run CSVMs, that inside will run a while loop of tasks to check convergence. So that's why you will have this long train of trees with dependencies. Yeah, the best way to look at this kind of application that have so many tasks will be to look at a trace. So that will be tomorrow, I think, the trace. And the graph, the dependency graph will be for applications with much smaller size, just to see how the tasks are interacting between each other. But if you want to see performance, you will need the PRACE. And that will be for tomorrow. So right now, we at that's it. I think that is the time. This is the end. So yeah, thank you for your time, for your attention, and check dislib at GitHub.